No more Bayesian puns, Vincent. No more Bayesian jokes.
Oh, well, Bayesian jokes are always welcome. By the way, Justin, can you check the whether the stream is working?
Yeah.
That would be nice.
I'm refreshing the
if it's working.
YouTube page.
If it's not working, we're still fine.
Yeah, it's working.
Okay, cool.
There is some delay, the usual delay of maybe a minute.
Yeah, probably well, it depends. It kind of depends on my internet. So usually the delay is about 5 seconds. But right now my internet is quite poorly, and it will be probably around a minute or so.
Yeah. I'll just try to listen to a few words there because I think there is some lag on the YouTube channel.
There usually is.
Yeah.
Yeah. No, I think it went better now.
Okay. Do you hear any echo or something like that?
No, it's nice. It's nice. It's all right.
Okay. It's very weird setup to kind of have this meetup and kind of the administration of the meetup and also the YouTube stream. Actually, the Google Meet has some functionality where you can create a streamable link within the Google Meet, but it's not visible outside of your organization. So, which makes it a bit not very useful for our case. But I suppose in something like universities or big companies where they have huge all hands meetings, it would be useful. So
someone owns a mechanical keyboard.
Oh, it's probably me. I'm sorry.
So the people who are on the stream and not in the Google Meet, I invite you to join us. So you can just easily join the discussions or the Q&A sessions and ask whatever you want without having to write it down in the chat box. And we are going to start in about a minute or two.
Yeah. I spoke to this HR guy that is organizing some conferences, development conferences, and he said that they calculated the degree to which human interaction dropped on online events, and it was terrible, like 80% or something. So people interact 80% less when the event is online. And it's it's I mean, we can all feel it. Usually we stay like 1 or 2 hours after the talks, and we laugh and we share ideas and everything. But when we're doing these things online, it's usually just a couple of questions. And I've been struggling with any ideas how to make this more social and invite more people to interact, and I really don't have any good ideas.
Have you ever played with Gather Town?
Yeah, that's the only thing that comes to mind.
Have you played with something? I've only looked at the website, and the website, the idea looks amazing, but I don't know what it's like. Like, have you played with it?
We had it for the summer school actually, but like it turned out that because of the schedule, like there weren't that many people on it using it.
Okay.
And also like some of the cooler features come if you pay. The
Right.
free version is somewhat limited, but I think conceptually it's pretty cool. Like it could definitely help. And I've seen so Workshop at Unrips are starting using it, and I think they're even considering using it at the proper conference.
So PyData Global is using it. And for people who don't know, because it might be, there's 2 people in this conversation who do know what it is. It's kind of like one of those Mario Zelda. You're kind of like a Zelda character. And if you move closer to other Zelda characters, then you suddenly get like this experience that you can talk. But it also means that if you walk away from a conversation, you can walk to another one. So you actually get these groups, right? That's kind of what happens.
Yeah.
That's super cool. Plus, you get to make your own avatar.
Yeah, and this is particularly they wanted when we talked, because we actually talked to the guys from GatherTown, because we wanted to know if they can they can allow us to use more features for free for the summer school. So we talked to them, and they actually, they're going to add features for doing things like posters. So it's not just that you can see a person, but there's a poster and you can see the poster, or you can see like a video from the pre-recorded video from that person. Because poster sessions now are horrible, at least at big conferences. Basically, there's a Zoom session where the author goes in and like nobody ever joins the Zoom session because you don't join unless you have a very specific question you want to ask. Or like it's a lot more awkward than in person, where you just go to a poster, you look over it, and maybe a question comes, or you just ask them to explain the poster. But it feels now that you need to have a lot more intention. You need to have a goal in the virtual format. So they're hoping to help with that.
I think they're also adding stuff like whiteboards and such that if you're with a group of people, that you can draw together on the same whiteboard, and all that stuff that you miss from real life, basically.
Yeah, that's what you miss.
Plus, you can
more whiteboards.
Yeah. Plus, you become a pixelated avatar, and you can look whatever you feel like. That's also kind of fun.
Yeah.
Kind of fun. Kind of. Okay, I just added 2 jokes to my slide deck. That's also done now.
Nice.
Great.
So, are we ready to start?
Yeah.
Okay. So let me just make a quick introduction, or Yasin, do you want to make the introduction first?
No, I was just going to invite you to make it.
Okay. Thank you. So, hello and welcome to everyone who joined us on YouTube or here in the Google Meet. I'm super happy to be here in the company of our speakers, Razvan and Vincent. And I hope this is going to be a great meetup. So this time we decided to try something different compared to our previous meetups. So everyone is invited to the Google Meet call, and they can join, they can ask questions, join the discussions, maybe sometimes interrupt the speakers. We'll see how it goes, whether they want that or not. But yeah, I invite everyone to kind of join and be part of the meetup to kind of have the true PyData meetup experience, so to say. So the links for that are, I believe, in the meetup page and on the Facebook page, and as well we have a link in the Google Stream chat box. So just feel free to join, and I'll add you to the call. Obviously, everyone is welcome to listen to the talks via the YouTube stream, and they don't have to join. And if they have any questions, they can just post it in the chat box. Yasin is going to monitor that, and we'll repeat the questions to the speakers. But if you would like to ask questions kind of offline not offline, but using the chat box on YouTube, I would suggest that you add a bit more context to your question. So when Yasin repeats it, it kind of makes sense. So we have an amazing lineup of speakers today. So first, Razvan will talk about data efficiency while training neural networks. And after that, Vincent will talk about his numerous open source projects and their application and inspiration to his job in RAS. So without further ado, I would invite Razvan to present his screen. He's a research scientist at DeepMind in London. He obtained his PhD from the University of Montreal under the supervision of Yoshua Bengio, he worked on different aspects of deep learning, particularly optimization and memory in recurrent neural networks. I will leave the rest of kind of his introduction to him, and enjoy the meetup.
Cool. Thank you, everybody. Hopefully now I managed to share my screen. So thank you for the introduction, and thank you for having me. So I'm my talk is going to be slightly on the theoretical side, but hopefully it's going to be interesting, and I'll try to keep it as intuitive as I can. So before I start, yeah, if you get confused or if you have questions, feel free to stop the presentation and ask questions, or questions at the end of the talk, or even email me. I'm going to go through like a bunch of results. Obviously, all of these results, they have a lot of corner cases and there's a lot more nuance. So yeah, I'm going to, just because I want to send a message across, I'm probably going to make relatively strong claims. So take everything with a bit of salt and not necessarily as ground truth. And yeah, I mean, the goal here is just sort of to stimulate discussion and interest in this kind of topics. Cool. Let's start. So I guess almost everybody is familiar with neural networks. So neural networks are these architectures that are formed by composing linear projections followed by nonlinear activations. One way to understand what they're doing, particularly if we're thinking about ReLU, rectifier activations, which simply, ReLU of x is 0 if x is smaller than 0, or x if it's positive. So it's this rectifier activation. You can think of it that what these models are doing is they're partitioning the space, and they're constructing this piecewise linear function. So if you can see my cursor, so this is an example of piecewise linear function, and the way what the learning process does, or what we're trying to do, is we're basically trying to adjust these linear pieces according to the loss surface, that to the boundary that we're trying to learn, right? So we're trying to find the best approximation. The interesting thing about deep neural networks is sort of the expressivity that they get. There's been a lot of discussion of why depth is useful for neural networks. This is this is actually a really old work on this. So there's a lot more newer work that are trying to exploit this more properly with less assumptions. But one way to think about it is what the neural net is doing at each layer is folding the space. Exactly like in origami, like in this GIF. So you can imagine that you have your input space, and now you're folding it in such a way. So each layer does some kind of folding in such a way that the decision boundary that you need to figure out at the end becomes easier. And this is sort of a toy example that that comes directly from that paper, where assuming you have this very complicated decision boundary, it turns out that as you're folding the space, this decision boundary becomes easier, and could potentially become easier and easier. And the point of the learning process is to find the optimal folding of the space, such that the final decision boundary that you need at the top is linear, because the top layer of your neural net is linear. And the other interesting thing about this is, if you're trying to look at the number of linear pieces that you have in this linear function, it turns out that by this scheme of folding the space, you can construct piecewise linear functions that have exponentially more linear pieces than if you have a shallow model. So one way to think about why the deep is important in deep neural networks is because they give you more expressivity, and this expressivity comes from this folding. So in particular, if anybody is interested, this paper, what it does, the only thing that it does, it provides a particular construction, a particular way of folding the space, showing that this will generate more linear regions that you can ever get if you have a shallow model. But this is just sort of one aspect of things. So it's really easy to get stuck in this trap and just thinking about the expressivity of your neural nets and what kind of functions they can represent. But what is important is to find the right balance between expressivity and learnability. So it's really important that the final system is still learnable. And the way we learn in neural nets, the basics of it, it's relying on gradient descent. And I like to have this slide. This is my mental picture every time I think of gradient descent. What is gradient descent actually doing? Well, basically, all it does is you have this nonlinear function, and you take a Taylor expansion of it. You take a first order Taylor expansion, so you approximate your surface by using a linear function by a hyperplane, and then you're trying to see, okay, how can I minimize this approximation? And because it's a linear function, we know how to minimize the linear function. But the problem is, the minimum of this linear function is going to be at infinity. If you jump at infinity, that's obviously not the minimum of the function that you care about. So what you have to do is you have to restrict your optimization to a region where this approximation is true. So one way to think about SGD is just basically saying, okay, find the line that approximates my function. Where is the minimum of this line? So this would be either at plus infinity or minus infinity, but then restrict yourself to a region where you trust things, and the region is usually done on the norm of the weights. So you restrict yourself in the circle. So basically what you're looking for is the point that the solution that you're looking for is going to be on the circle. So it's going to be either here or here, depending on where you go. And if you write down what this means, I mean, the first order Taylor expansion, so the linearization of your system is basically just L theta plus delta dl, and then you have this constraint. And if you use Lagrange multiplier to resolve this, and you work out what comes out of it, you basically get the typical SGD update, where this constraint gives you the learning rate. And then you get this process where you have to do this at every step, right? So what you do is you look in this small trust region and you look, okay, which direction do I need to move to minimize my function? And then because that approximation doesn't hold anymore, after you took that step, you have to repeat the process, and you keep repeating the process, and you get, this is sort of like the typical, I guess, picture that everyone has seen when they're thinking of SGD, and there are all this parallels that you can make with physics, where you have this ball that you let loose on a surface, and it's going to converge to a minima, pushed by gravity and like all the other forces that apply to it. So the issue with this, the issue that people used to have with neural nets, and why people were a bit skeptical about their ability to do things, is because our main way of optimizing them is relying on gradient descent. And if you take this this parallel to physics that I've just explained before, and you think you have a surface that looks as horrible as this one, depending on where you drop this ball that you let go to the bottom of the basin of attraction that they're in, you could converge to many different sub minimas, and many of those might be suboptimal, right? And it's been all of this kind of issue of gradient descent not providing any kind of guarantees of how you can converge to a better minima. And the advances that have been made on this front, and this is again, these are pretty old works. So this is again 2014, but there are a lot more works. The mode connectivity is much newer, and then there's a lot more newer stuff like the neural tangent and the LTK hypothesis. But like one way to think about this, so the original work that was doing this, the way they will argue is that when you over-parameterize, what happens is this surface magically becomes better behaved. And the way this was phrased in the 2014 paper was by making this connection to statistical physics, and basically saying what happens is, if you look at the error of the loss, so if you look at the error of the critical point that you reach if you let SGD run, and you look at the index of that critical point, where the index is the number of negative eigenvalues of the Hessian at that point. So what the index tells you is whether this is a minima or if this is a saddle point. In the saddle point, you have this mix of directions. So you have directions through which you can escape that critical point, and you have directions that go upwards. So I should have had maybe a picture of a saddle, but I'm assuming most of you are familiar with what a saddle is. But basically what this plot is trying to say, okay, if this is actually an extremum, if this is a minima, then the index has to be 0. If the index is not 0, then this critical point is going to be a saddle point. So what it means is that it has a plateau around it where the gradients vanish, where the gradients are zero. So that's why potentially your optimizer stops. But there are still direction you can escape. So there's still direction in which you can move. And the point, what this kind of experiments argue is, if you have a really large model, then you will notice that for really large models, all the minima, all the local minima, they actually have roughly the same value, and that value matches the global minima. So there were some results in statistical physics that proposed this for random Gaussian fields, and there is proper mathematical proof of why this happens under certain assumptions and so forth. And this is sort of the neural network variants of that, which this is just an empirical study that shows that there exists apparently a very strong correlation between this. And newer works, kind of build on this, and then you have results like the mode connectivity, where what they show is that if you start in different random points and you run to convergence and you get this minima, it turns out that these minimas are usually connected by an area of low error. So what that means is that when we're thinking about a minima for a neural network, we shouldn't actually think of it as a point. So people might probably have this typical ball in mind where you have a minima, which is the bottom of that ball, but that's usually not how they look. So these minimas are actually manifold. So they're in entire areas like this one that are complicated, and there is even some thought whether all of these minimas are actually connected to each other, and you have this very complicated manifold at the bottom, and your initialization and the noise and the stochasticity in what you're doing just basically gets you to a different point on this manifold. But then it doesn't matter because this is a manifold of roughly equal error. So these are some kind of theories that have been put forward. So there's newer stuff like the NTK. Yeah, so there is a question whether I can explain a little bit the eigenvalue aspect. So yeah, that is the so that's exactly what it is. So it's the semicircle law. So this was another. I just copied the plot, and I didn't actually need this, but there were two aspects of it. The other aspect was exactly this. So the other aspect was whether, if we look at the spectrum of the Hessian at these critical points, if they would respect the Vigor semicircle law. I don't know if I'm pronouncing his name correctly, but if it respects this particular law, and then what we've seen in practice is it does respect this semicircle distribution of the eigenvalues, but it's shifted according to the index. So what you'd observe is, sorry, not with the index, with the error. So there's again a correlation where, the higher the error, you get your eigenvalues to be shifted either to the left or to the right. And what happens is, if you have really low error, then everything is shifted such that all eigenvalues become positive. So it seems that there is this bias of where this is found. So this was another observation of the paper, that in principle, it looks like the spectrum of the Hessians, of the critical points, are respecting this distribution to a certain extent, so the way you'd expect it from a random matrix, but is shifted according to the error that you get in the loss. And it was, again, an empirical observation, and I think the original paper by Bray and Dean and Fyodor and Williams also connect to this, if I remember correctly, but it's been a while. So this was a paper that I worked in 2014, and some of the mathematical aspects of this statistical physics theory, they're not necessarily, I don't think I have a full grasp of them. But this was basically, the paper was mostly confirming that empirically the critical points of the loss surface of the neural nets kind of respect exactly the same observation that you noticed on this random Gaussian fields. So it seems that there is a parallel between them. And this has been pushed forward afterwards by Jan LeCun and Anna Horomanskaya, if I'm pronouncing her name correctly, in a paper that they tried to find a formal connection between neural networks and spin glass models, though there's something about that paper that I don't like. They need to make some really strong assumptions, which almost makes you think whether those are really neural networks anymore or they're completely different beast. But basically, I guess what I wanted to show with these slides is that there has been made progress in understanding. So there are like two sides of the story. So one is people believe that neural nets, you can't really work with them because you have this issue of bad local minima. They can appear anywhere. Like everything depends on so many things. And then empirically, like 2006, 2007, 2008, there were like results coming one after the other where, people just went ahead. They like, sure, there are worries, but let's just try things out and see what happens. And people run models on different data sets, different size models. And it seemed like this wasn't a problem, right? There is a study by Dumitru Erhan, I forgot the year, but anyway, where he actually, just looked to see what is the variance in the error that you get depending on initialization, on resampling your initialization point. And the variance is super low, right? No matter how many runs you do, like the variance, at least in supervised learning, tends to be super low. You usually get the same loss repeatedly. So there was a lot of empirical evidence that, even though we worried about local minima, somehow they don't seem to be a problem. And this work, starting with this work in 2014, but there are other works that were roughly at the same time, like the Jan LeCun paper, and then follow up with things like the mode connectivity, like the LTK and the NTK stuff. These are all different hypotheses that have been brought forward to explain why this isn't that much of a problem as we expected. And almost all of these works, the trick that they do, I mean, they're very different in nature, right? And whoever is kind of interested on this theoretical side, they're obviously really cool works to read. But the trick that basically all of this work use, or the claim that everyone is making, is if you over parameterize your model, then suddenly things are better behaved. And the trick that made neural nets work is relying on over parameterization. And I believe there is this, or at least there is this belief in the community that it's not the we're not using these big models that we normally do because they're so expressive. Like the expressivity study, like for example, the one that I presented before, is potentially meaningless because we need to over parameterize our models to a big degree just so that we can make them learnable. So the only way you gain learnability is by over parameterizing. So in general, most of the models that we're using are over parameterized with respect to the number of parameters that you actually need to represent the solution. I wanted to just highlight that, even though there are all these theories that are kind of nice and they have proofs and they're interesting, and I think people can keep building on them, there's still a lot of like weirdness to the loss surface. So I just wanted to, I had this feeling at some point, at least early 2015, 2016, there was almost this kind of belief in the community that, if you have a large enough model, everything is fine. You don't need to worry about anything. There are no bad local minima. All local minima are equal, which is kind of the claims that those papers are trying to do. But obviously, those papers, they come with a lot of assumptions and a lot of choices. And this is a paper that I'm an author with. It's a paper that's only on arXiv. It was never published, probably for really good reason, because it's sort of trivial and it's not that. But I find it very useful. And all this paper is doing is showing that is enough to have a finite data set, which we normally always have, to show that any neural network will have a bad local minima. So this is basically a paper that proves things by construction. And what it does, it says, okay, you assume the data set is finite. Give me whatever architecture you want of whatever size you want, as long as is finite. I guess as long as the model is finite and as long as the data set is finite, then it's very trivial to build to show that there exist really bad local minimas on the loss surface, right? And this is useful because it highlights this aspect that is sometimes kind of everybody knows it's important, but it's not always strongly acknowledged when we talk about learnability and we talk about these things, which is the initialization matters a lot. And if I am to rephrase some of the previous works, I mean, some of the previous works might already have said that in a way or another, but maybe not explicit enough. But if I am to rephrase that, is low surfaces are well behaved and everything is fine, as in a restricted region of the space, which is close to where we initialize. So if I'm thinking of like a Gaussian ball around where I'm initializing, yeah, in that region, like everything is fine, and all of the minimas that you can find within that ball, they're connected, they all have really low error, they're very close to the global error. But if I'm moving away from that region, then it's really easy to build up examples where learning would just be completely broken. And maybe this plot, I can explain this plot because it's trivial. The only thing you do is you can either play with the data or you can play with the initialization, but the only thing you do is like, okay, initialize your model or shift the data points in such a way that all your ReLUs are negative, or all the pre-activation to the ReLUs of your first layer are negative. And then there's not going to be any learning. There's not going to be any signal flowing through your model. SGD will not do anything. So where you start, that's where you stop. That's your local minima, and it's stuck. And this second case here, there are more interesting local minimas that don't exploit this kind of pathologies, but that you can still find them. The other thing that I wanted to point out, because I find it that's so kind of interesting, it might be completely meaningless, but for people who like theory, this is such a cool observation. So this is Belkin's work. So because he makes this claim, which is kind of obvious, but it wasn't to me until I read it. After you read it, it's like super obvious. But if you have neural networks, particularly with ReLU, like a lot of these things are restricted to ReLU because ReLU are easy to think about it. So if you have like a rectifier neural net, what you can do is you can multiply the weights on the first layer by 1 over gamma, and then the next layer by gamma. And if you do this, you're not changing the function at all, because if gamma is positive, because you're never changing the sign of anything. And then basically then this is exactly the same function. And this is one way to show that the minima cannot be a point. The minima has to be a curve, where you get the curve by playing with this gamma. And of course, there are more richer ways in which you can multiply things here and divide things there to get this effect. But the nice thing about this sort of very generic thing is it shows that the minima needs to follow the shape of 1 over gamma, right? When gamma is a positive number. So what this means is that this manifold, where you have the same error, is curved, which means that the function is non-convex. But it's not in the typical way that people think of non-convexity, but basically it says that in any neighborhood around the point, the function is non-convex. So it's never convex. It's never locally convex, right? Like you can't say, okay, if I zoom in close enough to my minima, the function is going to be convex around it. What is interesting about this, if you are, again, this is more for like theoretical people. What this means is that, well, all the proofs of convergence and everything from SGD, they all kind of break down immediately, because all of them are relying on things being locally convex. They always start by saying, well, you're going to move random, but at some point you're going to get stuck in this ball that is convex, and then you can analyze this as a convex problem, and everything is fine. And this is sort of how we typically think about MLPs and their loss surface and everything. We're borrowing most of the tools that we're using. We're borrowing them from the convex literature by just saying, well, there's a non-convex phase initially when you're jumping from one place to another until you find like a ball that is large enough, and then from that onwards it's just convex with respect to that, and you're going to converge to the minima there. But interestingly enough, that thing doesn't exist. So no matter how much you zoom in anywhere, things are non-convex. Whether this means more than that, I mean, obviously things work, right? So so things are fine. But what this means from a theoretical sense, I think this is still an open question. And I just wanted to point it out because I just find these things is more like, on average, things are fine. If you look in detail, like there's a lot of oddity with respect to neural networks and the learning regimes. And there's a lot more to be explored and a lot more to be figured out. I think now we have some tools to start analyzing these loss surfaces. We have some intuition and some theory of why learning still works, but there are still so many corner cases that we don't know why they're not affecting us, and a lot of oddity if you really look at the whole loss surface. The other thing that I mean, this is sort of the super typical thing that probably everybody knows. The other thing that I wanted to highlight here is basically the difference between optimization and learning, right? So, and the usual way that I'm thinking about is like, okay, you know, you want to fit some data, you can fit it with a line, you can fit it by a second order, you can fit it by a ninth order polynomial. I don't know if I have anything. No, that's basically it. And you know, obviously, if I'm looking at training error, the order 9 polynomial fits the curve better. Is this representative of the data? And I guess, you know, intuitively, if you just look at the plot and you look at the previous ones, you'd say probably the first one is the better one, or maybe the second one is good, but the order 9 is bad. Basically, what I wanted to highlight here is okay, I'm just trying to be aware of my time. I'm moving a bit slowly. What I wanted to say here is like, when we're doing machine learning, we care about learning. We don't care about optimization. So what we want is we want to find a solution that would generalize to new data points that we haven't seen. And this is not going to be reflected by the training set, by the training error. So yeah, I guess I phrased it there. Like, learning is about minimizing an intractable thing that you don't have access to because it requires you to integrate over the entire domain. So the way you do that is by optimizing some tractable approximation that you don't actually care about. So you never care about minimizing that approximation. We never want to get we don't care if we get the minimum of the approximation of we don't care if we get zero training error or not. What we care about is, are we going to generalize? Is this going to work on new observations that weren't part of the data? And this is what separates, that's another way of thinking about sort of the success of deep learning versus other methods. This is what separates neural networks, say, from other approaches, is not necessarily in their ability to fit high dimensional data. We can come up with other things that are equally good at fitting high dimensional data. It's their ability to generalize. So it's not that they're very good, you know, they're very expressive and they can fit all kinds of complicated high dimensional data. Is they're very expressive, but at the same time, somehow, when we learn them in the way we do with stochastic gradient and all of this, they tend to generalize really well. Yeah, so this is sort of, I kind of use this slide to just say that the universal approximator theorem, that I don't know if it's still being done, but usually kind of people throw it around of, why do we care about neural nets? Well, they're universal approximator, they can learn anything. The universal approximator doesn't mean much. So because we actually don't rely on this property at all when we do things, because what we actually want, you know, in some sense, we want to go against the universal approximator. We want to, for the optimization, to find a solution that minimizes the training error, that is restricted to the region of solutions that make sense, to the solutions that generalizes. And to deal with this, I mean, just besides relying on the natural property of neural nets of generalizing well, we also rely on regularization. And this regularization, okay, so there's a question whether I worked on AlphaStar. I haven't personally worked on AlphaStar, though I'm aware of what they've done, but we can go back to that after I finish a few more of my slides. Yeah, so one way to deal with this is regularization. So again, this might be something that a lot of people know, but yeah, the way to think about regularization is you're trying to restrict your search space. So you can think of optimization as a search strategy. So you have the search space of different thetas, different possible parameterization to get your function to do whatever you want. You have a particular way of searching the space. So this is done with gradient descent. But the problem is you actually don't care of minimizing the training error. You care about finding the solutions that make sense. So what you do is you come up with this way of restricting the safe space only to solutions that make sense. And regularization can be explicit. So this is this is like an L2 regularization. You can think of it as a Gaussian. You're basically saying, okay, if this is my loss surface that has these two minima, I add this surface, which is just sort of like a convex ball that has a minima 0. This is just my L2. And then when we add these two together, then I favor one of the solutions, right? I emphasize one of the solutions, the one that is closer to 0 than the other. And this is sort of how these regularization terms work. Another thing that people do is early stopping, which again is just a regularizer. And what you do there is you just keep track of how your model is performing on unseen data. And when you see that going bad, you stop and say, okay, this is the best I can do. And this is going to be the model I'm using. And this is sort of a very typical thing that you would find in any manual about machine learning. You have this underfitting, underfitting regime, good model regime, overfitting regime. So in black here is the training error, so how well you're doing on the data that you're observing. In red is the test error, the validation error on data that you haven't seen. And what everybody says is, well, initially you're underfitting, or if your model is small, you're going to be in this underfitting regime. As you keep training or as you increase the model size, you're going to get in this perfect region where everything is fine. And then if you keep increasing the model size, or if you keep learning, then you're going to go into the overfitting regime where things go bad. By the way, because of how HGD works, you can think of what early stopping is doing is basically restricting the area around 0 or around the initialization that you can reach, right? Because you're making these incremental steps. So if you're restricting the number of steps, you can almost think of a sphere and say like, okay, you need to find a solution within this sphere centered around where you started. So I wanted, again, like I think everyone is probably aware of this result, but there was this big discussion about it. So this is Belkin's work on double descent. So an interesting thing that is happening with neural nets is that this typical curve doesn't seem to hold. So in practice, it seems that as you increase the model size, you're not overfitting. Again, this is a very kind of interesting observation. I think there is a lot more to be studied here. This is something that's been observed empirically. So it's well known that you can make your model bigger and bigger, and it's just going to do better, even if the model is orders of magnitude larger than the data set that you're learning on. The intuition of the double descent, or what might be going here, it seems that the size of the model after you get over this critical point acts jointly with the gradient descent, somehow acts as a regularizer. So basically what Michal Belkin is trying to say in this work is that if you're in the extremely overparameterized regime, then SGD is bound to find the minimal norm solution. So it's bound to stay as close as possible to where you initialize. And because of this, you're not overfitting. So it's just sort of this coupling between the optimization that we use and the architecture that forces you to stay close to where you start. And that's why double descent is happening. And actually, interesting enough, this double descent effect, I think, happens in linear models as well. So it's not that specific to neural networks. It's just a regime that we probably haven't considered that much before, because particularly for a linear model, it almost makes no sense to go in this overparameterized regime. For neural nets is slightly different, is because we can't really work in the basically HGD fails if you're not in the overparameterized regime. And then we have this mix of things, this lucky mix of things where in the overparameterized regime, also we get this effect of not needing to worry about overfitting. So this was an interesting observation. Yeah, then there is this sort of interesting thing about gradient descent and stochastic gradient descent that I wanted to point out. So I guess everybody potentially knows the difference between them. So in gradient descent or full batch gradient descent, you use all your data to compute the gradient. This is sort of what the theory is built on. This is what you're supposed to do. In stochastic gradient descent, what you're doing is you're estimating this gradient by using small amounts of data that you sample IID. And the whole reason SGD was invented was to make things cheap, right? Because if you have a huge data set, trying to compute the full update on it, it's bad. But what is interesting about this is, and like it's easy to show that SGD, should somehow approximate GD. But what is interesting about this is that it turns out that if you train with SGD, you tend to generalize better than if you train with GD. And I think this on its own is just another quirk. I mean, technically, if you'd have a convex problem, if you'd have if you not have a neural network, but if you had a linear system or whatnot, then technically the kind of solutions that you find with GD and SGD, there will be no difference between them. But it so turns out that for neural networks, there is a difference between them, and that's sort of the interesting part of this. And the typical intuitive way of thinking about this is this idea of sharp versus flat minima. So this is, I think, firstly appeared in Schmidhuber, and Hochreiter had the paper about it in '97, but then I think it's a theme that kind of reappears regularly through papers, and so like a theme that's dominating this discussion of where why is SGD performing better than GD. And the intuition is usually that the noise is what helps you, right? Is the stochasticity, is the variance of the gradient. So what that helps is if you have a small, a sharp minima, so you have this small convex ball where the minima lies, if you have stochastic gradient, the noise in the updates would easily make you jump out of it, and you can only converge to this minimas that have a very large convex ball around them. Again, ignore the fact that there exists no convex ball and everything is non-convex everywhere. But this was before that work, and this was the way people were thinking about it. And this was basically just saying that the variance is the driving force in making SGD work better. There are some issues with this. So I put here a paper. I was part of that paper, which is it's very nice in 1D. It's easy to draw. It's easy to think about it. It makes a lot of sense. If you go in high dimensions, it turns out that we don't know how to define sharpness or flatness. We don't know what it means for a minima to be flat, to have a large convex ball. You know, people, and it's particularly weird because it turns out that, again, you can exploit exactly this gamma 1 over gamma trick. This is the original place where this trick, well, no, actually the original place is a paper by Ras Solokunikov. But anyway, this is an earlier paper where they use this trick. The point is you can use this trick, and what you can do is you can play with the spectrum, right? You can change the spectrum. You can make your largest eigenvalue to be as small as you want or as big as you want without changing the function. So there is some issue about flatness and sharpness. We don't know how to define them. So I'm just wanted to highlight that even if it looks very intuitive and nice, that there are a lot of question marks when you move in high dimensional spaces where we are. But it is sort of like a driving intuition of how things work. So I think it is something that it's worth for you to keep in mind. It's a good mental model of what's going on, as long as you're aware that there are issues with it. There is some new work here that it's also sort of interesting. So this is using, for people who been working a lot with ODEs, they use something, I wasn't aware of it before the papers, but something that they called backwards error analysis. I'm not going to go into detail, but what this paper is trying to show is that actually the difference between gradient descent and SGD is not just in the variance, but actually SGD introduces a bias, and this bias doesn't vanish. So basically, SGD cannot converge to the same minima as GD because of this bias term, which is not zero at the minima. And this is kind of interesting, and I think this is like a novel way, because so far people have been focusing so much on the variance and talking about, okay, you know, how this variance has to look like compared to the eigenvalues of the Hessian at the critical point. So like, okay, how this variance should be so that you can escape this minima, like how narrow this convex ball needs to be. But now it turns out that is not just variance that matters. There's actually a bias that never disappears. And then this basically says that, you know, SGD and GD cannot converge to the same thing because SGD has basically this bias in it. There are some assumptions that are used to get this, but the assumptions are actually quite natural. And it's interesting. This is a topic that explored. All of these papers are from this year. Many of them are at iClear, somehow separately trying to figure out this thing. And I think it's pretty cool that things that we thought we understand and things that we thought make sense, turns out that there's a lot more to them that we still don't know. And now, okay, moving forward. By the way, if anybody has questions, do feel free to interrupt. Moving forward, I just wanted to kind of converge to my take-home message. So this was a lot about sort of our understanding of how learning progresses and so forth. And I just wanted to make this note that the other thing that seems to be problematic with neural nets is the amount of compute. So this is a plot from OpenAI that looks the amount of petaflops that you need to train some of these really well-known famous architectures now. Like, you have AlphaZero, you have okay, this is a bit old, so I guess you could have GPT-3 somewhere here as well. I don't think they have something like that on this plot. But anyway, you have all of these famously known architectures. They all, the amount of petaflops, the amount of compute that you need, the amount of data that you need. Yeah, so model size, which we know we mostly need to increase the model size to make things more learnable, but then we also need to increase the data size. And the more data you have, it seems, things are always better. And the amount of compute that we need to have is better. And this is becoming really problematic. From my perspective, it's problematic for many reasons. Like some of these huge architectures, they're so hard to manhandle that it's really hard for you to do like the kind of ablation studies that you want. It's really hard for you to understand why they work, how they work and stuff like that. It also restricts the access to them to a large part of the community. So like smaller universities and stuff like that, they might not have the compute power to, train their own BERT model or whatever because it's too expensive, or do their own AlphaZero or whatnot. So it becomes really problematic. And like a third thing that I think should be more on our mind is also, this compute, it equals energy, which is contributing to the climate change. So it is like, for some of these experiments, if you think of the value that they add versus how many trees they burn, sometimes it's a bit worrisome of how easily we throw compute at things without actually thinking what is the underlying cost of this. And unfortunately, the deep learning paradigm kind of forces you to work in this large scale regime where you need to use so much compute. Even if, so that's a bit problematic. And I wanted to talk about like, okay, so then what we need to do is we need to think of ways of making learning more efficient. I think it's actually extremely important, and it's important to do that, and it's important to understand why learning is so inefficient as it is now. And I wanted to present an observation, and it's based on RL, but you don't really need to understand RL for this. It's just, this is where it happened, this work was done. So I'm just gonna have like a slide or two on RL just to give you like a big picture thing, but you don't really care about RL. This is a much more generic result than that. But the point of this, the point of RL is, is this interactive system where you have an agent that is trying to learn to solve a problem, but the way it can solve the problem is, it gives an action to the environment, and the environment tells it, it gives back an observation or a reward. And the key thing here is that there's no fixed data set, right? The data comes from the interaction of the agent and the environment. So if the agent doesn't know what it's doing, then it's not going to observe anything interesting, because it's not doing anything meaningful to observe those interesting things. And this is one of the key components of RL that makes it so different from everything else, is this reliance on the interaction between the agent and the environment. And deep RL, it's just having the neural net being the agent and providing the actions. This is sort of like the kind of things you can do with DRL. So this is a simple, a simple agent that is trying to navigate this maze and pick up apples and stuff like that. So it's a really interesting domain. It's more generic than supervised learning in some sense, though it tends to be way more data inefficient, less practical, and so forth. But it is sort of like a potentially a quite generic framework in which you can express any kind of learning problem that you want. So that's why people are so interested in figuring out how to make this work better. So DRL, because it is even worse than supervised learning in terms of data efficiency, in terms of the amount of data and the models that you need. It's a place where people have been thinking about this. I mean, everywhere people have been thinking about this, but people have been thinking about this quite a bit. And one potential solution that people have been investigating is whether you can use multiple tasks, right? If you have multiple tasks together that you need to learn anyway, is there any kind of form of sharing knowledge between them so that you learn faster? Like, you don't need to learn the same things every time you learn. All of these tasks are related. They're happening in the same environment or whatnot. Maybe if we learn them jointly, things are going to go better. And this is a strategy that's been used in supervised learning as well. People do this quite often, and there is some success in this space in just trying to learn on all tasks together, but it doesn't always work. And I think this is something maybe that not everyone is aware. I think there's this kind of intuition that, okay, if I put everything together, it's going to work better, but it doesn't always happen. So you have, you can have task interference, you can have task dominance. So when you have task interference, it's basically tasks are fighting each other, and you end up not learning. You end up learning them much slower than if you'd learn them independently. Or you have task dominance, where you put 3 tasks together, and at the end, the system knows only to solve one, because that one dominates all the others in terms of the norm of the gradients or whatever other form. So there are issues with these approaches, though there are successes. So these are successes in RL. Because these slides were borrowed from an RL thing. There's lots of successes in supervised learning as well. And in RL, people have been even doing auxiliary losses, which these are basically just self-supervision. They're in my book, they're the same thing, but this is the RL terminology, and self-supervision is computer vision terminology that is now expanding into NLP and any kind of supervised thing. But yeah, in RL, we call this auxiliary losses, and is this place where people are coming up with auxiliary losses such that you learn faster, right? You put these auxiliary losses around you that you optimize jointly with the true loss. So that's not exactly how people do it in vision, where they use the self-supervision to pre-train the model, but I think that's just a minor detail that is not that important. And the thing that I wanted to highlight here, this is one of these very successful papers about auxiliary losses. And the auxiliary losses, if you look at them, they're ridiculous. So they're like, sometimes they don't even make that much sense to you. So like here, the idea is, okay, we have this 3D environment, we have the RGB, we have the visuals, and we know the distances. We have a depth map that we know the distance to every object in the scene. And the idea was, okay, if I do depth prediction, if I predict how far away the objects are, would this help me to learn faster? So this sounds like a typical self-supervision task. And it turns out that if you do depth prediction for the whole image, because you have a per pixel depth, that doesn't work. That just breaks. So what you have to do is you have to pick this band in the center of the screen. You have to split it into 6 or 8 squares, if I remember correctly, and then you have to discretize those values to be between 1 and 8, and then you do basically just like a classification for the depth. So you have to simplify these things ridiculously much, such that the auxiliary loss actually helps you and it doesn't hurt you. And there's some other auxiliary losses that are proposed in this kind of works that are, I mean, they're not completely meaningless, but again, it kind of just highlights that is not, anything that might make sense to you. If you throw it in, like chances are it's not going to work. You actually need to explore different options until you find something that works. And in this work, this is the work I wanted to talk about. So this is the work with Tom Scholl, Doina Joseph. So we call this Ray hypothesis or Ray interference. We had this observation. We started with this typically in RL, and then I'm going to say that this works in supervised learning as well. But now in RL, so in RL we were kind of very aware of this fact that the data that you observe comes from the agent, and it depends on how the agent is interacting with the environment. So we're saying like, okay, in supervised learning, what happens is when you start, you have a lot of learning signal, right? The errors are large, the gradients are large, and it tells you like you have to move in this direction. In RL is not the case. In RL, when you start, your gradients are super small because you're just randomly moving your hands around. You're not doing anything meaningful. So you're not observing anything about the environment that makes sense. So it takes a really long time until you start behaving somewhat meaningfully. And then once you start behaving meaningfully, you start seeing some learning signal. And once you've seen this learning signal and you start learning, at the end, like the learning signal decreases because you're close to a solution. So there's not that much to learn. So in RL, you have this kind of shape, this inverted U shape for the strength of the learning signal. Again, this is a very high level concept. I'm not talking about gradient norms or anything. I'm just talking hypothetically about the learning signal. And then we're interested in what happens when you train on two things simultaneously, when you do this kind of multitask thing. And particularly what happens if you have interference. And what happens is, by chance, one of the tasks is going to do better than the other. And as soon as one task is doing better, it's going to push the other one through the interference lower. And because the task is pushed lower, like the performance of you're regressing on that task, this means that the learning signal of that task becomes weaker and weaker. So what this happens, let me see if I have a plot. Yeah, what this happens is that even though you're showing both tasks to the system, you're learning them one after the other. So, no matter where you start, you either learn task one and then you learn task two, or you learn first task two and then you learn task one. And there's no way around it. And maybe this is the only slightly funny bit of my talk, is that the reason we call this the ray interference or ray hypothesis is because we were starting to doing this kind of plots, and we realized that they look like a ray fish. So we said, okay, this is a really good name. So this has nothing to do with with the actual what's going on there. But basically what this suggests is, when you have, and you see this kind of plot in supervised learning, and I'm going to talk about this, when you have this kind of plots where you look at the loss and it has kind of like a waterfall. So maybe because for some people this would be confusing. In RL, you usually maximize stuff instead of minimize stuff. So in supervised learning, this will start high and go down. In RL, they usually start low and go high, but it's the same thing. It's just one minus the other. But when you have this kind of like waterfall kind of structure, this waterfall kind of structure potentially comes from this kind of ray interference that we're talking about. So, and in RL, it's very typical to observe this in multitask scenarios. It's typical to observe this in a single game scenario. And the reason why that happens is because any single game can be decomposed into subtasks. So, even though you think you're not doing multitask, you are implicitly doing multitask, because, say you're learning some data, that data, there might be different modes of the data, the pictures of cats and the picture of dogs and the pictures of whatever other animal. So you are learning a multimodal data, and you can think of each mode as a subtask, or each group of modes as a subtask. So you have this structure internally as well. This is a supervised learning scenario where we notice the waterfall from a paper. I think it's not that atypical to see this kind of waterfalls. There is an interesting paper that I should have cited here, really old paper, about the dynamics of deep linear models from Andrew Sachs and co-authors. I forgot who else was on the paper, where they actually proved that for deep linear models, you have this waterfall. And this comes, again, is because of the depth, because the input of any layer is changing over time. So you can think of it as almost like an RL task, where you have this non-stationarity of the data distribution. Like the data that layer 2 observes changes over time because the weights of layer 1 are changing. So you don't, you can imagine that it creates the same kind of dynamics that you see in RL. Where if one task dominates, it kind of destroys the representation of layer 1, such that task 2 cannot learn anymore because it doesn't have the information it needs, because it's been overwhelmed by the information task 2 needs. So what I wanted to say about this is the strange thing about multitask. So we've been thinking a lot about multitask as a solution to this, but the strange thing about multitask is many times you do multitask and you actually learn the task sequentially, which is very, it's not what you'd expect. That's not what you're trying to do. And it's interesting because that's how humans learn. And it's also interesting because there's an entire field called continual learning that talks about how can you learn tasks sequentially, and who argues that learning tasks sequentially is way harder than multitask learning. And I think this is where things are connected. So in continual learning, we're trying to learn one thing after the other, and the idea is, how can you do this in a reliable way? And usually you have a list of things that you'd hope. You'd hope that you learn task 1, task 2, task 3. At the end, you know how to solve all of them. This can be done with a single model of fixed size, so you're not doing something weird where you're learning separate experts and you stitch them together at the end or anything like that. And you'd hope that learning things sequentially would help you, that learning one task will help you to learn the other one. And like most of the work in continual learning, what they're trying to do is they're trying to mimic the multitask loss. They're saying, oh, actually what I want to do is to learn task 1 plus task 2 plus C, but I don't have this term. So what can I do about that, right? And you do weird kind of things. You think of it from the regularization perspective, or what you do is you say, well, I'm going to take these terms that I don't have, and I'm going to approximate them by some Taylor expansion. This would give you EWC. You can approximate them by different things. This will give you different terms. But basically, all regularization methods are trying to approximate these terms that are missing. Or you have modularity approaches where basically this is more the stitching aspect. Where you just keep like a different expert, and then you find a way of either distilling the previous experts into your new expert, or make sure that you can read what the other experts are thinking. But and then you have memory-based stuff, where in memory-based stuff, you basically you keep track the other tasks by keeping track of data from them, but you just try to keep track of as little data as you can. And because multitask learning kind of works and it's able to learn, people, when they do continual learning, they focus on this idea of do not forget. Like, how can I learn all of these tasks one after the other so that at the end I still remember all of these tasks? And this is sort of what dominates this literature, and all of these approaches, they're mimicking multitask learning because multitask doesn't forget, and it's trying close to it, and it's just trying to reach that point where it doesn't forget. But I think what actually we should be thinking about is, again, if we're looking at gradients, we should be thinking about something else. We should be thinking of why, when we do multitask, we end up learning sequentially, and why none of these models are data efficient. And the high level picture that I have in mind, that I'm kind of excited about right now, is assume you have a mini batch. Like, let's go back to the gradient, like super basic stuff, and you're looking at the gradient on a weight, and you have a bunch of examples. And the average gradient on the mini batch is the average of the individual gradients. And you can think of each gradient, I mean, they have values, but let's ignore that. Just assume they only have a sign. Some gradients would be positive, some gradients would be negative. And the way you can think of this is, you can think of this as a tug of war game, right? That's depicted here. Like, each example is trying to push the weight towards itself. Increase, other guys are pushing decrease. And at a high level, I mean, you can go over task, you can go subtask, you can go about modes of the data distribution. But basically, the way SGD works is it at every step, it generates this tug of war games where everybody's trying to push the weights towards themselves. And the only way learning happens is by finding an equilibrium, right? Is as soon as everybody starts pushing, depending on with what force they push, at some point you'll end up at the equilibrium, which will be the weights that work for you. And this tug of war dynamics, this pull and push that each example and each task and subtask and mode of the data is doing, this is how neural nets specialize their units. This is how credit assignment is being done. By credit assignment, I mean how you decide which weight is to blame for which loss and stuff like that. Which weights are supposed to encode what a dog is, and which weights are supposed to encode what a cat is, and like how these different features are happening. So all of these are happening through this tug of war. And this is the reason why data needs to be IID, because this tug of war, for it to have sense, it means that all the different modes, all the different tasks need to be present at the same time and pulling on the rope. IID kind of ensures that, right? IID says that in expectation, all of them are present equally, so they can all push on the weights as much. And this also highlights that there is no explicit knowledge composition, which is quite problematic. So the way you learn about things is not by reasoning about the things you've learned before, but just by having all of them jointly pulling on the rope, rather than composing on what the other learned. And catastrophic forgetting, or this forgetting, is basically just a failure of doing credit assignment. It's basically what happens if you take one of this guy out, then you pull off the rope, and whatever that guy was trying to represent through the pull that it had disappears. So yeah, so I think this is sort of my take-home message, is that when you're talking about continual learning, when you talk about sequential learning, what we actually are talking about is how do we do credit assignment in learning? How do we decide which weights are supposed to encode what? And the way it's being done so far using gradient descent is through this tug-of-war dynamics. And this tug-of-war dynamics is what leads to data inefficiency, because even though I've learned something, I still have to see it. I still have to compute gradients on it, because otherwise I lose that pressure, and then the tug-of-war dynamics doesn't make sense anymore. There's plenty of works that show that there are examples that you learn through the first pass through your data set, or even before that. But even though you've learned about data, you still need to evaluate on it. You still need to compute gradients on it. Even though you've learned a task in a multitask scenario, you can't just remove that task. As soon as you remove it, everything breaks. And this is sort of one big source of data inefficiency in deep learning, is the reliance on this particular kind of dynamics to do credit assignment. And if we come up with a different way of doing credit assignment, I mean, that would be amazing. So there is a question saying, does that mean that each neural network classifying cats and dogs has to learn a lot of mini tasks, like classifying a cat ear or a leg? Yes, I think you can always. So the one thing that I would be worried about is aligning the subtask that the neural net is doing along things that are semantically meaningful for us, like thinking about what a cat, like first finding what a cat nose is versus a dog nose is, or whatever. But it is like learning about different directions of variations in the data, of like, okay, if my image varies along this axis, then it's more likely to be a cat than there is a dog. But you can definitely decompose you can definitely decompose the learning process about learning different things, different mini tasks. I'm not sure whether you can argue that that segmentation into mini tasks is always going to be semantically meaningful to a human. It might be, if that makes any sense. Like, and it doesn't always have to happen, right? But it happens at least in complicated tasks. But especially if you see this kind of waterfall, um, looking of your learning, then there's definitely different things are happening every time you hit a plateau and every time you escape a plateau. So every time you hit a plateau and you escape it, you can potentially decompose the problem that way. Let me see if I have any. This is just a summary of what I said because I've taken too long. I'm not going to go over it, but basically just saying what I said before. Yeah, I just wanted to highlight that I'm part of this EML community that I've been organizing with Doina and Viorica for the past, I think now 3 years. We have a summer school, we do workshops, we have a website, and we're just trying to encourage the machine learning community within Eastern Europe at large. So yeah, if there's anything interesting there, go visit the website or go see the Twitter. And thank you. And if there are more questions, if not, I'm done. Okay, so there is a question that says, what is your opinion on transfer learning in the context of efficiency of learning? So yeah, I mean, I think transfer learning is a tool that we want to use in order to induce data efficiency. I don't think we're that great at it. I can talk a lot about things that don't work with transfer learning. Particularly in RL, things are really messy once you get there, but in supervised learning, there are problems as well. Maybe I want to highlight something that maybe a lot of people are not thinking about. It is we don't know how to measure transfer learning. I think that's the biggest problem. Like there are people measuring things. Those things potentially are meaningless, as in, transfer learning depends on the learning process that you use when at the test time, and like trying to remove that dependency is actually quite hard, and it kind of messes things up. So just to give you an example, I mean, this is not pure transfer learning, but something maybe that people are familiar with. If you think of MAML, right, which is super popular meta learning thing, at test time they use SGD, right, and MAML works better than if you do SGD on multitask. One interesting question is what would happen if you do like a Hessian tree or a second order optimizer, starting from the multitask solution or starting from the mammal solution. My intuitive guess is that you probably can get multitask very close to perform as well as mammal. And then, so mammal is performing better than multitask learning under the assumption that you're going to use a particular thing at test time. And I think we need to think a little bit more of what that means and how that affects all the kind of conclusion that we draw. But yeah, in general, I think, yeah, I think it's close to the meat of it, but yeah. Yeah, so there's a huge family of approaches, and I think without details, it's a bit hard to know exactly what would make most sense for you. But it depends on what. So one thing that I can say is, like, if you think about rehearsal kind of approaches, it turns out that you need ridiculously less amount of data to rehearse something that you've already learned or to maintain that performance. So rehearsing is not as expensive as actually repeating the full big task. But that's one approach. There are like regularization kind of approaches that you can use, where you kind of build kind of trust regions that forces you not to move too far away from where you learn. There is a long list of papers, but it depends on the kind of things you like, the kind of things that make sense for the task you have, if you can have access to the original data at all or not, stuff like that. But yeah, I'm happy to discuss more, like if you send me an email, or if you want to talk now, I don't know, more in detail. But yeah, depending on the scenarios, there are many approaches that exist and probably many new things that can be done.
Okay, so if anyone has any questions, you could just unmute yourself and ask, or you can use the chat as you did before. And I'm sure Razan will be happy to answer. So our next talk will start in let's say 5 minutes. So if anyone wants to just grab a cup of tea before that, now's the time. And during these 5 minutes, I'd suggest if anyone has more questions, they can ask. Or
so I also want to go for tea, but I also want to ask a question. So I'll just go real quick.
Okay.
So how do you over-parameterize a linear model? Is that you just sort of start with a wide data set and you have lots of variables? Or what do you mean with over-parameterize a linear model?
That's a good question. I remember Michal Belki mentioning this. I forgot what he did. I'm imagining you can do something like you project to something very high dimensional and then you project down. So you have two linear operations one after the other, which technically are the same as a linear model, but I don't think that would. I mean, I think he's just. Yeah, I think he's just talking about, like, if you have your input, you project it to high dimensional space, and then you learn something linear on top of it, but the projection is fixed. That's probably the kind of thing, because his whole double descent thing is centered around like minimal norm stuff. So if you look carefully at his argument, it kind of borrows a lot of ideas from random projections, where it says like, okay, you're projecting things at a very high dimensional space, and then when you're learning, you just need to find the useful ones in that huge set, and that will give you the minimal norm thing. So I think
it's like a regression, but only a few of the regressors matter, kind of that idea.
Yeah. So I think probably when he referred to linear models, he probably referred to something closer to things like random projection. But I don't remember fully the details. I just remember I was just kind of copying what he said in one of the talk, that he said that even in linear, or he has a claim where it's not just deep nets that have this property of double descent. You can see it in, I guess, in that kind of setting.
And I just have a technical question. Can you share your slides somewhere?
Sure. I
can.
Some
really cool and useful.
Yeah. I can send them to you, and then I'll probably post them on my website as well. But I'll send them to you, and then you can disseminate them through mailing list or whatever you have.
That would be great. Yeah. And also thank you for the very, very nice talk. I forgot to say I was really happy to learn some stuff that I've heard before, but I didn't really understand completely. So thank you.
I'm going for a tea real quick. So
Okay.
Yeah, it was a great presentation. I also very much liked. There were some technical details that are sometimes overlooked in different presentations, and I really enjoyed kind of looking into that.
Thank you.
Thank you.
Yeah, and sorry, yeah.
Sorry, great talk, by the way. Just two quick questions. So first is there a general like push right now for like better generalizers versus good optimizers? Say Adam is a very good optimizer, but a couple of years ago it turned out that it generalizes more poorly than say SGD or I don't know, SGD with momentum.
Yeah, I mean, it's like people are definitely picking the learning algorithm based on how well it generalizes. So with what you said, I think there is a sort of a push especially in some places of people not using Adam but actually using SGD with momentum because it does better if you tune it properly, whatever that means. But I think in terms of generalization in general, when people think of it, they usually phrase it as regularization. I mean, it's usually phrased as regularization, but you have things like you have, I think it was Anna Horomaskaya, a bunch of other NYU people. I don't know if Jan was on that, but there's this entropy, what do they call it? Entropy HGD or something. Anyway, where they're looking at the entropy. I forgot what they're looking at, but they're basically trying to find flat minima according to some definition of flat minima. So it borrows intuition between this sharp flat minima, and they try to phrase this as a regularizer that you throw in on top of your SGD, and you can think of that as a SGD. There's been works like with this implicit regularization stuff that I mentioned, that SGD has this different term compared to GD. You know, people have thought of like, okay, if this is how the terms look like, let's just add it and put a beta in front of it and try to hypertune that to see if we can do better than what SGD is doing. And people have been playing a little bit with this. I mean, this is very new stuff. But yeah, I mean, I think people are kind of cautious when they phrase these things. So they would always refer to this as regularization because conceptually it's easier to sell and easier to think about it than rather saying that I have a special optimizer that generalizes better.
Yeah, sure, but my point was more going towards this data efficiency. So you have a very good optimizer that learns faster, but at the same time it generalizes more poorly. I don't know.
Oh, yeah. I'm not necessarily aware of I mean, I know people. No, I'm not necessarily aware of exactly what you have in mind. I think people have been looking at like meta learning and other kind of things, but not necessarily exactly what you're saying. Yeah, I see what you mean now, but I can't give you an example of this.
Yeah. Okay. Thanks. And the other one is you basically show that the more parameters you have, the better you, at some point, right? You behave. But there is now also some push, to be able to do like machine learning on smartphones and Jetsons and stuff like that, and even smaller devices like Arduinos. So of course they try to distill this knowledge. Is there like some work on like, is there some loss in generalization where you try to like distill this knowledge into a smaller model? Or is it only important in training time? This is my point. Like,
yeah, so it's a hard I think there's no clear answer. I mean, I can give you some intuitions, though I don't necessarily have a paper now to back it down. I think for things like, I mean, in general, you lose some performance whenever you compress, no matter what you use. I think there is some evidence that if the task becomes more and more complicated, then compression will do worse and worse. So it might be that some of the high-end things, like I'm thinking sort of like GPT-3 and so forth, they might not be exactly in this, or they might not be as over-parameterized as we think, or they might not be in this regime because it seems like this kind of systems are not that easy to compress as, say, like an ImageNet, which can be compress something that's running on ImageNet, you tend to lose. I don't know of any. To be honest, I don't know of any kind of compression techniques that argue that you can compress a system without losing any bit of test error. I think it can be minimal, but you always lose a little bit, which maybe answers your question. I don't know if that answers your question, but yeah.
Yeah, maybe even more in general, like network architecture search for like a specific architecture where it can perform, say, at the same order of accuracy like a much bigger model, but much faster, obviously. Otherwise,
yeah, I mean, you have I mean, depends on who you talk to. So like there are people who would argue that, I mean, this is not architecture search, but like they would argue that GRU would perform as well as an LSTM for its similar amount of parameters, but not the same amount of parameters, similar number of hidden units, but GRU is actually cheaper because it has less gates than LSTM. And I know that for that reason, sometimes people prefer GRU just because they tend to be cheaper. There are some of these trade-offs, I guess, sometimes, but yeah.
Okay, thanks.
Okay. So if any of you have any more questions, I'd suggest we continue with this after Vincent's talk in the discussions afterwards. And for now, I'd like to introduce to you Vincent. He's a contributor and creator of a lot of open source projects that you might have used before, like Scikit-Lego or Human Learn. And he's also working at RAS. And I will leave to him to kind of finish this introduction about himself and his talk.
Okay. Perfect. Yeah. Like I'd be really surprised if there's a lot of Human Learn users, mainly because Human Learn is a week old. So like if there's any users out there, I'd love to hear it, but it's kind of new. One thing I would prefer, if that's possible, if one of the co-organizers could leave their webcam on, mainly because that way I kind of have a feedback mechanism if I'm going too fast or if the jokes aren't working. So if I could see like the webcam of someone during the talk, that'd be good, because then I have a proxy. Thanks. But yes, my name is Vincent, and I always like to talk a little bit about open source, and the easiest way for me to explain how open source works is to just talk a little bit about this tool called SPSS. Now, I just want to check, there's two people on the webcam. Do we know what SPSS is? We've maybe used that in college. It's this click tool. And it's useful because you don't need any code. And the idea behind it is actually not too bad. The idea behind it is that if you need to do a certain type of analysis, no need to do very complicated code stuff, you can just click a button. And that might automate a whole bunch of things. And especially if code is intimidating to you, this is actually not a bad idea. Like a lot of people want to do basic linear regression, and putting that behind a button, it's pretty good. But then you try to use this in practice, and then you get into these interesting situations. So like the basic linear regression example, let's just try to predict a house price. And let's say we've got square meters of a house, we know the number of bedrooms, we know whether or not it's an apartment, a house, or like a mansion, and then whether or not it's in a city and a village, and we use all this stuff to like get ourselves a proper house price. Well then, you can do this with linear regression, and if that's the thing you're interested in, you just click the button and you're done. But let's now say that we work for a company who's interested in not necessarily getting this one number out that's the most likely. Let's say that we're a company who likes to deal with risk, like most companies that are dealing with financial things like house prices. In that case, you want to get kind of a distribution as output of a model. And then you immediately hit a problem where if there's no button here for give me a histogram as output, then you can't have it. So very early on in my sort of career as an econometrician, I kind of noticed this happening over and over and over again. And it got kind of annoying because at some point I was surrounded by colleagues who really understood the solution, but couldn't apply it to a problem if it was not compatible with their solution. So that made me think, you can't use SPSS in practice too much. There's a limit. And I don't do exercises in Jupyter notebooks. I try to solve problems in real life, and real problems are messy. And the main sort of conclusion I immediately had was they always require some form of customization. It's never the case that you can just pick up a Lego brick, put it on top of something, and then, you know, people will pay your fee and you're done. There's usually a lot of maybe boring integration work that needs to happen. But the main conclusion is that customization is the main feature that we're maybe interested in if we're interested in solving actual problems out there. And that's kind of the beginning of the story on how I got started with these 2 open source packages. Again, Human Learn is just a week old. Like, if there's users, I'd love to hear it, but I think it's not too many. But the reason why I didn't like SPSS is also the reason why I really like scikit-learn. It's built in such a way that it's really easy to customize. And I don't mean that in the sense that the tools that it offers are great. I kind of mean in the sense of, if there's tools missing, it's pretty clear and obvious how to maybe add your own. So just to give a couple of examples of things that I was able to add in this ecosystem. So if you download scikit-lego, basically what you get is you get a lot of separate tools that you can use to customize whatever machine learning pipeline you already have. So one thing that you typically do is, let's say you have a binary classification problem. And you probably want to have some sort of separating line here, right? And what you can say is that if this is a logistic regression, then on this axis over here, you kind of get this logistic curve, something like, it's not a good logistic curve, something like this. All right, so it's 0.5 here, it's like near to 1 here, it's like near to 0 there, let's say, and that's how you separate these 2 classes. Well, then one thing that you might want to be able to do is you might want to say, well, that classifier, that logistic regression, that kind of works, but maybe I want to move this threshold a little bit to the right, or maybe just a little bit to the left. And the reason why that's interesting is that's a really convenient and, to be honest, lightweight tuning knob to get like higher precision or higher recall. Typically, if you move it in this direction, then you get higher precision but lower recall. And if you move it more in this direction, well, then you're probably going to get all of these yellow points, but you're not going to be very accurate at it. So one of the things I would really like is sort of a decorator around whatever scikit-learn classifier, but such that I can specify the threshold. So what we offer in scikit-lego is this customization option. What you can do is you can use something that's known as a meta model. And a meta model is basically just a estimator, but it accepts another estimator as input and then adds behavior to it. That's how it works. And in this example, it's using a logistic regression, mainly because everyone knows what logistic regression is. But nothing is stopping you from doing this with a support vector machine, naive Bayes, or something like that. And what's really sweet is that this threshold value over here, that is something that you can grid search over as well. So even if you know nothing about how the model over here works, if you want to tune it for precision and recall, this is just a really convenient way of doing that. So here's a plot that you can find on the docs where, indeed, if you move the threshold a little bit to the right or to the left, the main thing that's changing is precision recall. But if you play your cards right, you can also see for the textbook blob example I just showed you, you can also get the accuracy just a little bit higher if you're interested. And again, I hope it's pretty clear that this is something that's kind of reasonable. You might want to use this, but SPSS is not going to give this to you. You kind of have to make some of these tools yourself. But scikit-learn makes that relatively easy. Another thing that we added in scikit-lego, it's another estimator, another meta model, so to say, is instead of saying, well, we move the threshold around, we allow you to specify a group. So normally when you do a regression like this one, so to say, you can say, well, there's a dummy variable. And then when you add a dummy variable, basically what you do is you have a constant that's being added as a value. But what we also allow is we allow you to say, well, if you, instead of adding that as a constant, you can also say, well, that's a grouping parameter. And for every group, I want to train my own separate linear regression. That's also something that we allow you to do. And again, it's a customization option, but one that's actually kind of practical in real life. Very often, the effect of being in a group is not that you add a constant. That's usually not sort of how the world works. But if you're able to maybe make a model that's really specific to a subgroup, yeah, that can be kind of good in practice, especially if you're in industry. Like a final meta estimator that we added there that I thought was kind of cute. Very often you have like time series like this, where if you look at the most recent data, it at some point simply just doesn't resemble the old data anymore. The world moves on, especially if you're in Corona, right? Then these lines tend to go down, and you really have to be careful that you're not overfitting on the history. And these sorts of things are, I think, are pretty interesting and funny, because people always say, oh, you have to use as much data as possible. And then you meet these people in industry that seriously use data from 20 years ago because that's more data, right? Like that stuff happens. So we thought we should make a tool for that. And the tool we kind of came up with is yet another meta model. And it's based on the parameters, sort of on the, that's based on the merit of the fact that some of these scikit-learn models, they have a fit XY. And then I think it's like a weights parameter that some of them have that you can pass along. And what we do is we say, well, the weights parameter that go in here, we can have that be determined by something that's like exponential smoothing. And then you can pass an axis, probably time, such as you can say, the stuff that happened more recently, just give that more weight than the stuff that happened in the past. And the way that you scale and weigh that is yet again something that you can grid search over. The thing that I find funny about this one is it's a pretty good idea, but effectively by doing this, you're making your training data perform way worse than your test data, which is the most counterintuitive thing you imagine. But I hope it makes sense, right? You will see training data perform way worse than your test data. But again, the main joy that I hope to sort of explain here is that you can customize this sort of thing to your own pipeline, to your own custom problem. It can very well be the case that this sort of decaying over time effect is not something that's in your sort of domain, but it's nice to be able to use it if that is a problem that you have. And I think a lot of problems in real life have something that's like this. There's a whole bunch of other tools you'll find in here as well. I think we've added like 52 components at this phase. We also accept people from outside. Basically, if you can convince me and this other maintainer that you've got a pretty good idea, we'll gladly maintain and host it for you. As long as you also add some unit tests. That's the main thing that we add for. So one thing that we also have is lowest regression. It's one of those models that are actually kind of useful. It's just that not a whole lot of packages have it. It's basically a more, it's kind of like a theoretically better k-nearest neighbor in a way. Another thing that we have is we have this thing called a Patsy transformer. If you've never used Patsy in Python before, it's effectively what it allows you to do is it's based on R. So you have this formula syntax that allows you to sort of define what columns to pick from the data frame. What it automatically does is it checks what the types are. So if B is something that's discrete, it will automatically make one-hot encoded variables available for that. But what you can also do is you can say, well, I don't want to have a constant value added, and I want to apply a function as well. But this string is also something that you can grid search. So that means that in your grid search now, you can also say which variables are supposed to be tagged along and which aren't, which is also super useful. Another thing that we've added is this notion of a fair classifier. So as you might have heard, this whole fairness thing is kind of getting worrying. So what we figured we should do is maybe also have support for some classification models as well as regression, where you can say, well, I want to optimize for accuracy subject to a certain limit on the fairness. Like I don't want my fairness constraint to be over a certain threshold, but given that threshold, find me the best model. And we allow for some different definitions of fairness. But also, if that's interesting, the scikit-learn API, I'm not going to go in depth in how exactly you can customize your own objects, but it's fairly easy to add these things yourself. So this is something that SPSS will never allow me to do, not in an easy way in any way, but the Python ecosystem and the scikit-learn ecosystem definitely made this relatively easy. The thing I want to add, though, just as kind of advice, should anyone ever want to sort of do this on their own, this is the mandatory Lego joke. Most packages that I make, what I try to do is I try to stick to the Python, I guess you can call it like a tradition. In Python, if you type import this, you're going to get this wonderful poem that the authors of the language learned while designing the Python language. And in the same tradition, what I try to do is whenever I try to make like a library like this, I try to get the creators together, and we also try to write a poem. But that's kind of a thing that we add as a little sort of kind of as a bonus. And it's also a nice way to get early contributors in, because people who make like a significant contribution, when we try to, like if they've really added something big, then we say, could you please add like 1 or 2 rhyming sentences to the poem? And people kind of like that as a little gift. And I am legally required to also mention this poem, so here goes. If you go to Scikit-Lego and you import this, the first lines of the poem are, roses are red, violets are blue, naming your package is really hard to undo. Haste can make decisions in one fell swoop. Note that Lego is a trademark of the Lego Group. It really makes sense. We do not need to bluff. Lego doesn't sponsor, authorize, or endorse any of this stuff. And you can read the rest, but it follows. Like, it gets more serious after this. But what I will like to say is, like, there's also a cultural aspect to making some of these tools. So, when in doubt, if you have a Python package, add a poem. So the idea that we had when we designed the Scikit-Lego thing was just, hey, there's a couple of tools missing. And it kind of became this smorgasbord of tools in essence. We basically added anything that we sort of made us go, well, that makes sense, let's just add it. But at some point you're in this field for like 5 years and you take a step back and then you kind of think, well, you know, there's some other stuff maybe wrong with the ecosystem and that actually fits in a theme very well. And that got me thinking and inspired to make this this other project called Human Learn. It's literally like 2 weeks old. I presented it last week for the first time. But the idea that I had here was, in the last couple of years, we've been in this transition where before we took data and then we got, I don't know, someone with domain knowledge to come up with some rules, and that would give us an automated system to make labels. But we've recently sort of transitioned into this other way of thinking where instead of us determining the rules, we should just supply labels and data and have machine learning figure that out. And there's merit to going in this direction because you can automate way more, right? But machine learning does have this, it's kind of naughty in the sense that it can pick up a pattern that we don't want. And especially if you think about themes of fairness, but also themes of artificial stupidity versus common sense, these machine learning models really aren't perfect. So I was wondering, you know, what can we do to make this interaction just a little bit better? And the easiest way for me to explain it is to sort of talk about this use case. So let's say that you're World of Warcraft, right? And you can download this data set and come to this conclusion yourself as well. Well, let's say you've got all the session data of all of your players. You've got, you know when they log in, you know when they log out, you know if they're a level 70 warlock, and you know when they're a noob. Like, all that information is known to you. Can we predict who will keep playing? And can we predict who will churn in a month? That's a very reasonable, business-driven sort of use case. You can do your machine learning thing what you want, but I can also say, you know, if there's a player that was playing at like 12 o'clock on New Year's Eve, instead of being outside with the fireworks and like socializing, then odds are this person is very interested in playing the game, and then I don't need a machine learning model to tell me that that person's probably going to continue on playing the game. So for that subset of people, I don't need a machine learning model. I can just pretty much tell already what's going to happen. So wouldn't it be great if we can sort of think about machine learning maybe more in this way, where we can say, you know, I've got this rule that is going to add, it's going to function as a safety mechanism in a way. And we're going to say, if this rule applies, then this is how you're supposed to handle it. And otherwise, we'll just give it to the machine learning model. If I think about like industry and how people like to deploy these things, it is really nice to sort of just have these guarantees, right? And a lot of people nowadays, they first make the best machine learning model, and then afterwards they try to sort of hack all of these safety mechanisms around it. But I kind of figured it'd be interesting to see if we could just maybe do this from scikit-learn. When I really started thinking about it, I actually came up with another use case where such a thing becomes quite useful. Because these decision trees are kind of one-directional. It's kind of like a case-when thing. You can say, if you're a child and your income is way above average, yeah, then we should probably get like a tax audit your way. The children aren't supposed to make that much money. And if you've got 10 bank accounts, then also you're in the risky category. And I can come up with lots of these if statements. And then finally, maybe we do the machine learning model. Another way of looking at this is to say, well, for the easy cases, we don't need a machine learning model. So it also means that what we can do is we can maybe start benchmarking against common sense. Instead of trusting the machine learning model, we can also ask our department of domain experts to come up with a model, and then our machine learning model can sort of benchmark against those things. Another observation that I had was another safety mechanism that we might be able to design is that we use machine learning models inside of these rules. So we might be able to say something like, you know, if in production we detect that X is an outlier, then don't automate the decision because this is data that our model shouldn't be able to have good judgment on. Like it might be that this is so far away from the bell curve you don't even hear it ringing. That's sort of the joke I usually make when it comes to that. So if we detect an outlier, then we do certain behavior. If the associated probability value is too low, then we also have a fallback scenario, and only then do we take an automated action. This is also, I would argue, reasonable design. So I've made some tools to hopefully make this just a little bit easier. What I've made is something that's known as a function classifier. The way it works is you just take whatever Python function you have that performs the prediction, and then I take the keyword arguments of that function. You have to declare it here. That's kind of important, otherwise everything fails. But by doing this, you can effectively turn any Python function you have into a scikit-learn classifier that you can grid search over as well. And to me, this feels like the most flexible way to define business logic. If you want to do basic logic, a Python function doesn't get more simple than anything else. And what's kind of nice about that is that you can also use that in combination with existing classifiers, assuming that I've already got this outlier detector thing and this classifier thing. What I can just go ahead and do is inside of this function, I can use those to make maybe what I alluded to earlier, like diagrams like this. I can also just get in here and I can put that in a function classifier, and lo and behold, it's scikit-learn compatible. I can do grid search and all that good stuff. Another thing that the library tries to do is, you might have seen this GIF over this week. But what I've also figured is maybe something that makes it hard to define rules is also the user interface. Because you want to have maybe business domain people make sort of drawings that say, yeah, this feels like a risk category region, and this might be better. So one of the features that I've added is you're actually able to draw a machine learning model. I think it's a clever trick. What we effectively do is we keep track of all of these polygons that you draw, and then we can figure out whether or not a point is inside of a polygon or outside of it. And here you see one chart on 2 dimensions, but you can make many. And effectively what we do is when we see a new data point is we count how many polygons it fits in, and then we do sort of a weighted average to figure out what class it might be. A benefit of doing this is that you can sort of do your exploratory analysis while also constructing your benchmark. What I really like about this is that you're not going to just do fit predict and call it a day. You're actually doing a little bit of exploratory analysis here. So if there are like obvious outliers, then you'll see them at least. And another thing about that, suppose that I actually define these regions, and I can also use that as an outlier detection mechanism. If a point doesn't fall in any polygon, it's probably an outlier. So these drawings can be used for multiple things. So that's also a thing I've added to the library. The whole point of the library is to just make it easier for you to write your own rules. And again, what I hope is really clear is that if this doesn't exist in SPSS, then SPSS is not going to give that to me. But if I think this is useful, the Python ecosystem allows me to make these tools, and that customization is something that's really precious and really, really awesome. Speaking of awesome, this library also has a poem. It's a little bit different, but I'll read you the final, to give you an impression of what I hope this library will be someday. What I'll just do is I'll just mention the final couple of lines. There are many ways to solve a problem, but don't let fancy tools get to your head. Why would you use a predefined solution if you can create a custom one instead? And to me, at least, that's kind of the core of what I usually try to do. Yes, deep learning algorithms, they're amazing, right? They're fancy. But if at some point I find myself understanding the solution better than the problem, then I usually think I'm doing it wrong. And it's sort of been a guiding principle that I've been able to keep in my career, which I'm really thankful of. So I've talked about these two examples. Scikit-learn basically led me to this path to make these two tools. But recently I have done a bit of a switch of careers. I am no longer a consultant, but what I try to do now is I try to focus more on NLP. Like we try to make conversational systems. And what I kind of got to do is I got to talk about sort of assistant technology, kind of what might it look like to design a conversation and then build tools for that. Before I go into this, how much time do I still have?
How much time do you need?
I mean, people want to be home at some point with their partners, right? So let's do I have like this was like what 20 minutes? What I've just done?
Yeah, more or less. Yeah.
We can do a demo. We can do a demo. All right. Okay. So what I'm going to do now is Scikit-learn is obviously something of an easier problem than designing a digital assistant, right? I mean, Scikit-learn literally is fit predict. We have X, we want to get Y out. But a conversation has different aspects to it. It's not it's one thing goes in and another thing goes out. So what I'm just briefly going to show is what a Rasa project looks like, so we can sort of see the moving parts that we're typically dealing with. And it's not a full tutorial, but just to give a bit of an impression. We need something of training data. So the way Rasa tends to think about this is, well, you usually have something like an intent. Like it could be that right now, my intent is to say hello. And there's different examples of saying hello, right? There's different ways of me being able to make it clear that I'm interested in greeting you. In this case, what we're looking at, by the way, is a chatbot that functions as a text-based adventure game. So one of the other intents that you might want to have is you might want to look around in the room or look around at an object. This is a little bit different because we have an intent at some point in time. So this is what we want to do, but there's context that we have to keep in mind as well. You might be looking at something, and then the thing that you're looking at is something that I'm interested in. Similarly, if you want to purchase something, that's great, but it'd also be nice to know what the thing is that you want to start buying. So this is the training data, so to say, that we typically have, but this is only part of a conversation. This is only one sentence. But I can take this greeting and this looking as Lego bricks to construct a conversation. And for that, we have this other configuration file where we have stories. And you can see that the greet intent is a Lego brick that I can use to define the flow of a conversation. So I can say hello. And then this is the action that's supposed to be triggered. And then if after saying hello and getting this action back, then a user might have said help. And then I need to trigger another action. So there's examples of all of these things under the hood, but I hope that we agree that there's not just this from text to intent prediction going on, there's also this dialogue management happening over time of the conversation as well. And that's sort of a dimension that makes this problem quite a bit harder. What Rasa allows you to do, though, is it allows you, just like in Scikit-learn, to construct a pipeline. And typically the pipeline has like a tokenizer that takes your text and splits it up. We have a featureizer, something like regex maybe. We have count factorizers. We've got lexical features like part of speech that we might be able to get out. Typically, we do character n-grams as well. And then we have this object that's actually kind of important. Then in this case, we also have a machine learning model that takes everything that's happened in the pipeline and uses that as input. And that's typically how a bare bones hello world Rasa bot is created. And one thing that's important to keep in the back of your minds is just like in Scikit-learn, all of these components are in the end Python objects. So when I started working at Rasa, I kind of started looking at their stuff and I kind of started wondering, you know, I'm here to support the research team. Can I maybe do Scikit Lego human learn kind of things, but for NLP? Because there's definitely like something there, right? I mean, NLP is a hard problem, but part of the problem is tooling and a good user interface and that sort of thing. So what I would like to do now for the remainder of the talk is just show you some things that I've been working on in this space, also to hopefully inspire you to help me, because there's a big problem that I'm currently facing, which I hope you'll all find amusing. So it's the demo time. So just as another quick overview, what does Rasa do? Well, effectively what we do is we offer machine learning tools in an open source way that do this whole detect the intent, detect the entity, and pick the best action to do. And these situations can get quite complex. For example, if someone is saying, hello, I'd like to buy a pizza, we're in a flow of a conversation, then a user can sometimes break the flow by saying things like, by the way, are you a human? And then we require these assistants to recover from these interruptions as well. So there's a couple of aspects to this that are actually not necessarily super obvious. And immediately, you kind of come back to this need of customization, because sure, I can give you an algorithm that sort of solves all of this, but the question is, can we come up with an algorithm that's general enough, or is it maybe easier to just make a system that you can customize? Because if we think about entities and how you should detect those, right? I mean, detecting a postal code is really tricky. You can't use a regex for that if you have postal codes in multiple countries. I mean, I guess you can still regex to some extent, but you want to guarantee that it goes the way that you like it. So customization. We also have these situations where we have a chatbot and there's a human handoff that needs to happen. Now, human handoff depends on your backend system, so there's bound to be some integration work. So again, there's customization needed. There's ethical concerns. We never want to see a bot made with Rasa that pretends to be a human, and that is something that we really like to see as a guarantee. So we want to have a system where you can have that in as a rule, as opposed to where that becomes something that hopefully the machine learning pattern picks up. But mainly the thing that's tricky is that customer service is not the same as a bot that does frequently asked questions. I thought that it might be a similar problem, but there's too many domain-specific aspects to it that this is really, really not the same thing. In fact, a frequently asked questions thing in US English tends to be not the same thing as a frequently asked questions thing in UK English, simply because of the cultural difference. Different questions are being asked. The order in which people ask certain questions is different. And these are not things that the algorithm will pick up. These are data quality issues that you yourself have to realize as well. Dealing with entities and intents might certainly be different per use case. Entities that are very specific also tend to happen. So you might want to have your own custom spacey model that you trained up front that you want to combine inside of Rasa. That's a use case some people have. But I think currently, and also what I'm interested in as far as customization goes, you're often dealing with non-English, and this is actually kind of a thing. A lot of the tools that we currently have are hyper-focused on English, I think. And the thing is, I've only been in NLP for like half a year, but I think that's because the data has always been the most available there. But if I think about, all the use cases that we have, it would be a bummer if we design systems that are benchmarked only on the English language. That's, I think, currently one of the harder things for us. We have a couple of international benchmarks. Like we also have I think I recall a Spanish data set, a Thai data set. So we benchmark our algorithms also on non-English, so to say. But it's really hard to generalize. And we kind of need a community of people around us to remind us what does and what doesn't work. So the point that I hopefully am priming you more towards is that, yes, Rasa works because we allow for customization. But something that I was wondering about is, can I maybe support both my research team as well as the community if I kind of do the same trick? If I just kind of start thinking about some tools that I can make around Rasa, where there might be some holes. And the idea behind this is we also have private data that we cannot share to the outside world. So it's going to be hard also for, let's say, companies to give their data to us so we can benchmark it. So instead, what we're going to do is you can throw crazy ideas in my direction, and I'll try to add support for Rasa. So what I'll do now is I'll just show you some of the tools that I've been building. Some of them are really specific to Rasa, and others are not. And I'll show a basic project just to get the ball rolling. There's a project that I've recently created called Rasa NLU Examples. And the whole point of this project is to add components that in the config file that I showed earlier. But I want to add components that are available for non-English use cases. There's a bunch of tools in here at the moment. We have this. There's a tool called Stanza, which is from Stanford, that has tokenizers, which are pretty sweet because I think they have like support for 60 languages or so. And what these tokenizers do is they also add part of speech information as well as lemmatization. We have a Thai tokenizer that we've recently added, but also I've added support for fast text as well as for byte pair embeddings. I'm not sure if people are aware of byte pair embeddings. What they do is a pretty cool trick where fast text kind of takes all the n-gram characters and tries to encode those. These byte pair embeddings are basically subword embeddings, but they do this clever trick to cover a lot of ground but not need too many tokens. The main thing that's also pretty cool about them is that they have been pre-trained for 275 languages. So yes, I have support for Bulgarian word embeddings, which is pretty sweet. That said, I already had that in fast text. So there's actually 2 sources of embeddings that if you want to play with them, you can just go ahead. So let me just check. That's the byte pair featurizer. We talked about Stanza. One thing that I've also added recently, and I don't want to suggest that this is per se a really good idea, but again, it's about the fact that you can customize. I've added support for GenSim. So theoretically, what you can do is you can also train your own embeddings. And here's why that's actually both a really smart idea and a really dumb idea. I hope that we can imagine that it's great to have these pre-trained word embeddings, right, for fast text and, whoops. I hope that we both agree that for fast text, it's great to have those around, and byte pair embeddings, that those are also great to have around. But typically, word embeddings are trained on Wikipedia. So if we think about properties of Wikipedia, right, it's really historical often, and it's really formal. If we think about conversations in chatbots, they're usually really not in the past tense, and they're usually very informal, and they also usually have spelling errors. In any way or form, I hope you agree that the way that words flow in Wikipedia doesn't resemble a conversation. Now, I recently discovered that there's this data set, the Open Subtitles data set, and apparently there's this data set where you have subtitles for movies that span from like the 70s till now, and like proper gigabytes of that stuff. And it's a bit of a crazy idea. But if you train on that, then maybe you have an embedding that represents a conversation better than anything trained on Wikipedia. So I don't want to suggest that this is technically something you must do, but by making this available, at least some people can try. And this way, people in the community can say, well, I know of one person who wants to do this for Polish, and that person can then report back to me. And I think this way, we can at least learn these sorts of things together. I think it's going to be, if nothing else, a more interesting way of learning how to do these conversational agents than for me to keep asking for data sets. Another thing that I've started building, this started as an educational project, but then people started using it, is this project called What Lies. At some point, I noticed it was really hard for me to explain to people what information actually is properly encoded in these word embeddings. So what I figured I should do is just make this unified API where we can allow you to say, I want to have embeddings from TensorFlow Hub or from BytePair or FastText. And we just have this layer of abstraction where everything just works the same way. And we allow you to make pretty visualizations and ask like interesting questions. One of the features is that it's actually a little bit more easy to make visualizations on bias inside of word embeddings. It's something that we try to make a little bit easier. If you go to the documentation page, you'll see a blog post explaining why debiasing techniques in general don't seem to work. Topic for a different talk. Something else that we also have is we have scikit-learn bindings. So what you can quite easily do is if you use a language backend that is made available inside of What Lies, then you can just stick that in a pipeline, and then it's a scikit-learn compatible component. Text will go in here, and the embedding for that text will go out. Currently, we support Spacey, fast text, byte pair, universal sentence encoder, GenSim, TensorFlow Hub, and Hugging Face. Not everything from Hugging Face and TensorFlow Hub is supported because not everything is eventually an encoder, but we think this is enough for people to start experimenting and playing to figure out what sort of patterns actually exist inside of this library. I want to zoom in on one pattern in particular, mainly because it's sort of assumed as truth, even though it isn't, but also to give like a demo of what the library can do. What I'm doing here, I'm saying, please give me the fast text language, and that's the backend, and here's the name of the file on my hard drive. So I'm basically saying, pick up English, please. But that's the only thing I'm doing. And then I have a language object. What a language object allows me to do is it allows me to say, well, please fetch me a word like man. This is an object that has a vector attached as well as a name. What I can also do is I can say, well, please do that for not just man, but please do that for man and woman. And then I kind of have a data frame of these embedding objects. What I can then do is I can make this public API where you can turn this into a NumPy matrix. But what I can also do is I can say, well, there's these plotting methods that I just make available based on this sort of data frame object that represents a collection of vectors. There's a bunch of interesting things that you can do with this. But one of the things that I really like to play with is I can also say, well, please give me similar tokens back. So I can say, well, here's the embedding for king. Fast text language, please give me vectors that are similar to that. Based on Euclidean distance or cosine or something like that. And then, you can see that king is similar to king. But what I can then also do is I can say, well, please take king, let's subtract from that man, and let's add to that woman. And we can literally see what lies in the word embeddings. Because apparently, when you take king, you subtract man, and you add woman, you get king. Not queen, that's the closest. And when I saw this the first time, I was kind of like, what? Is that whole analogy story, is that hype? And you can kind of play with it. One thing I really love pointing out is that originally, before we did all of this arithmetic, king was closer to queen. Let me just lock that. So this number over here, that's the distance from king to queen. The number over here is the distance from whatever this arithmetic is to queen. And we see that king is closer to queen before the operation than after. So this whole analogy thing, right? Using this library, you can use it, you can try this out in all sorts of different language backends, and you can come to the very quick conclusion that it's actually kind of fishy. That's the point of this library. The point of this library is to make it easy for you to play with this. I have a theory on what's happening. My main theory is, if you consider this vector that I'm subtracting, and if you consider the vector that I'm adding over here, to me, it's plausible that those two vectors are definitely in the same cluster in embedded space. And therefore, it's also very plausible that I'm taking two vectors that are similar and just canceling each other out. Which kind of explains why the order of words that I've got over here isn't that different from the order of words that I've got over here. And that means that I can also do stuff like this. I can subtract fast and add slow. Order doesn't change. Again, it's a theory, right? I'm not suggesting this is a proven method. My main theory so far is that when you add a vector and if you add a vector and subtract a vector that's similar, my theory is that it's just noise. There might be some more stuff happening, of course, here, but the goal is that you can play around with this and that's just made more easy. That also means that if you have your own freaky embeddings, that this is sort of a toy that you can play with. And also all the images are sort of paper quality, so you can definitely do publications with it as well. There's some interactive visualizations and stuff that are all really cool to play with, but I hope also here, the main point is I kind of like this idea that Rasa is also going to have this ecosystem of tools that you can easily play with, where just like in scikit-learn, I can customize more and more to stuff that I like. What I'm also doing as part of my job is I try to explain some of this NLP stuff. So if people are interested, why is debiasing super hard? I have this YouTube channel. It's part of my job nowadays to actually maintain this. What I also do is I take requests. So if there's any content that you think I should be making on non-English languages, like reach out to me. I'd love to hear what's missing right now. But what I'm also doing right now, I mean, if I'm honest, I started this NLP journey not even a year ago. So what I'm also doing now is I'm starting this project where instead of making a chatbot on my own, I want to start doing that with the community. So the first chatbot that is public that I'm building with whoever wants to join is Breakout Bot. It's an adventure game where you have to escape from a room. So there's an inventory system. You can pick items up. We have to detect those items. And this is, I think, a project I want to do together with the community because it's cool to make a chatbot that talks, but it's cooler even to make a chatbot that listens. So this is one of the first, there will be many projects that I intend to make, not on my own, but with a group of people, because I'm pretty sure that me being an experienced adventure game player, that I'm going to experience this differently than someone who isn't, right? So that's something that we have to do together, I think. There's also some Streamlit apps that I'm making to make it easier for you to play with trained Rasa models if you're interested. It's called Rasa Lit. So there's this environment where you can send text and we will automatically detect the entities and make pretty charts. Also for grid searches. So if you're using Rasa, definitely check that out. But the main point, and this is sort of the conclusion that I hope to kind of leave you with, is I very often found myself in this situation where, you know, deep learning, super fancy. We're in this, what a time to be alive. We have all of these algorithms. But I've usually at clients been this guy. I've been the guy that said, you know, I've been looking at the problem for a while and I understand machine learning algorithms, but there might be this lovely little hack that will just fit this problem really, really well. And I've noticed that a little bit too often, too many times, these kinds of people were sort of in the same room and that they were sort of saying things like, oh, but that's not even AI, that's not data science, you shouldn't solve the problem that way. You need tensors to be flowing and that sort of thing. But especially when you're making digital assistants, and that's kind of the whole point of sort of how I see open source as well. Whenever you do data science, you have this data that you optimize for. And let's do that in a Venn diagram. This is kind of like whenever you run grid search, then you run it on a data set that you have. But especially when I started making chatbots, what I really learned was that the data set that you optimize for isn't necessarily the data that your users generate. If you come up with if you're really accurate on 6 intents, but none of those intents are ever used by your clients or your users or if you're a digital assistant, then they're meaningless. Then it makes very little sense to have them in your data set anyway, because you're optimizing this part. Instead, what might be better is if we start focusing on this part and this endeavor of figuring out what our users want in the first place. That's not a quantitative thing at some point. It's more of a qualitative thing. So if I think about tools that I'm making for non-English users, sure, embeddings are cool, but I'm a little bit more interested about tokenizers. I think tokenizers are, like, if you don't have a tokenizer, then it's already game over. We should make sure that we have those first. So what I really would like to do is just ensure that this overlap is big. And at Rasa, we're also making labeling software for free. So it's called Rasa X. Definitely play with that if you're interested. But if I take a step back and think more about community, I really need to help people to help me understand what tools are missing for languages that I do not speak. So it's a bit of a pitch to all of you out there. But if you're interested in learning more about NLP and you're interested in building chatbots, there's this thing called Breakout Bot. Just join the fun. Hit me up on GitHub, and we'll do something. But if there are tools missing for Bulgarian or any other language, that's what I need to hear. And especially if some of these tools don't work, it's going to be really hard for me to do all of my benchmarks on your data set. But I love making tools available for you, and I think that that's also the way forward if you're an open source company, which is great. And I don't have a poem now. Like, this is the the end of the talk.
Okay, thank you very much for the talk. We already have a few questions in the chat, so if you can look at them. I have a few others, but I'll wait because I came up with mine after I saw the ones written in the chat.
Okay.
And I just want to preface, hi everybody, Krum speaking. So I asked the first question, but it was just before Vincent asked that other languages are kind of interesting. So this, I mean, German or Dutch versus English, I think we can leave it for the discussion.
So I kind of need to draw this. Hang on, I've got this fancy drawing tablet. So let me just slide back, kind of that. Right. Do I have an empty slide somewhere? Yeah, that's empty enough. Okay. So if I understand the question right, the transfer learning, no, not that one. The question is, how different is an NLP task like training a chatbot in a language like German or Dutch versus English? So there's this interesting phenomenon. Let's say that you don't have a whole lot of data just yet. So you're just starting out, you have a couple of intents with a few examples. Well, then it might make sense to have word embeddings around, because even though you don't have a whole lot of data, those word embeddings might compensate. Even though those word embeddings are trained on something that's more general than what your specific use case is, there might be something to gain. But what we kind of do at Rasa is we have this diet classifier, and one aspect of how that works is, let's say that you have your input over here, which is this sparse array with just count vectors. I mean, effectively that gets passed to a feed-forward layer at some point, and that gets passed to a transformer at some point. And, you know, somewhere at the end here, we've got the labels that you're making yourself, right, for your specific use case. So you could argue, even if you don't have embeddings, you will have latent representations that are being trained on your behalf anyway. So maybe instead of worrying too much about, oh, English is better because they have better embeddings, what you can also do is say, well, how about we just focus on our training data first and foremost and just focus on that? Because if you have way better labels and more data that you've collected from actual users, odds are that the embedding you'll get from doing this is more relevant to your use case than whatever pre-trained thing from Wikipedia.
Mm-hmm.
So yes, there's definitely like there's spacies around, so there's definitely like more tools for English. But I wouldn't want to suggest that you need to be English to have a good digital assistant. We've noticed that this trick with some count vectors tends to actually work kind of okay.
Mm-hmm. Okay. Yep. Thanks a lot.
Then the question is, what's the link for this? I don't know.
I think the this at that point in time was what lies.
Yeah.
But
so if you just type what lies into so what lies Rasa, if you just type that into Google, then you'll find it. There's a documentation page with lots of features and guides. Give that a Google. You mentioned you transitioned into NLP recently. Can you please describe your process into NLP transition? I would love to describe that. However, I must admit it's bad life advice and it's really hard to replicate. Because here's kind of what happened. I went to this conference last year, the Spacey in Real Life conference. If people are aware of Spacey, there was this lovely little conference in Berlin. I was really impressed by it. And there was this moment during the training session where everyone could sort of present what they did during the training day. I did a presentation. People thought it was entertaining. And then kind of what happened during the bar moment after the conference, we went from like a really busy bar to a bar that wasn't that busy. So I went to one of the Spacey core developers and I said, this bar is way better because it's way more spacey. You know, as a bad joke. But the thing is, that was like a memorable thing. And as the night later progressed, they kind of came up to me and said, "Hey, Vincent, you seem like the kind of person who would YouTube really well. Would you be willing to sort of help us make some training material?" And I didn't know the first thing about Spacey. That's why I went to the conference. So I kind of said, you know, if under those circumstances you're cool with me making content, I'd love to give it a try. I've never done that before. But from their perspective, it was like, we have someone who's enthusiastic about this, and, you know, you can explain. And it's actually kind of better if he doesn't know anything about spacey, because then he can make content while learning, and that's going to be better than if an expert tells you how to do it. So I started hanging out with them. I've made 5 big videos on YouTube. I do that in my spare time. I'm currently waiting until version 3 comes out before I make another series. But that's just something I've started doing on the side. And then at some point, Raza was hiring for a research advocate. And then it turned out that the CTO was a fan of my blog, and then I got hired. That's a simple story. Like, it's really hard to replicate. But my best advice is just go to conferences and like tell bad jokes to people. That's usually that's usually how my career progresses. And I take my work serious, of course, but community is definitely the way to go. PyData.
Thanks a lot.
Yeah, go PyData.
It's not a surprise because I'm here. But yeah.
Yeah. It's a great community. It's a shame that we cannot go to bars anymore. I think the very last event that we made in person, it was in a bar, and it was a great event. We had
a spacey bar.
It wasn't very spacey, but it was a craft beer bar, so we get some.
Oh, okay. Beers. I got points. No, but it's like, the best advice I guess I have for people who are interested in maybe pursuing other parts. I mean, just make sure that you're super enthusiastic about something, and when you're sure that you're enthusiastic about something, just make sure that other people notice. that tends to be pretty okay. Like, commit to open source once in a while, talk to people. It's not magic. That's kind of how it works.
Okay, I have a few comments about your talk. It was very, very, very nice. The first part when you mentioned, the Lego stuff and the rules stuff. I mean, that's something that I personally have done on so many projects myself. Some of the tools that you showed. So for sure, I'm thinking about integrating them. And Georgi is smiling right now because I've been his team leader, and he knows that I don't do anything by myself, and usually people do it. But yeah, I've done it too.
Actually, I'm smiling for another reason. I was thinking during the talk, Yasin very much likes those kinds of drawing your own rule set of how should you in a way you should classify your data or build your system. He very much likes building a rule set of doing things, so that's why I thought he might enjoy this.
Yeah, rules rule. Yeah.
Literally.
Yeah. So that was very nice, and I just wanted to tell you that you have inspired someone. At least you inspired me today. And about the Rasa tools, one of the things that people do in NLP is, when they have many languages, they tend to cheat. They use machine translation to just translate their inputs in the other language, so they can just work in any language because there is Google Translate to anything and from anything. And I would say that similar to what you present with the Scikit Lego, you can introduce a translation tool somewhere in Rasa, so that you can still do the same cool things with evaluation and testing that exist in Rasa, but after a translation phase.
So I don't have much experience with it. Like, I'm part of a community, so I hear stories about that. I have heard stories that the whole translation thing, that's a little bit of a mixed bag. A large simple reason is simply that you can translate something from like Dutch to English, but try translating a joke. Like, it doesn't always work that way. There's cultural differences and stuff, right?
That's my second point after the translation. Yeah, that's exactly right, and usually that happens because right now we are trying to deal with translation of chats. I mean, person-to-person chats in our domain, which is hosting, and in our case, it is customer support. And there are some funny things that happen if the person says, let me check that for you. The translation thinks that you are asking for permission, but you're actually, just being polite. And the other thing, when the person says glad to have you over, glad to have you over at our live chat system, it's somehow translated to glad to have you ended, like glad to end you. That's not very polite, and there is always this kind of jargon. I think we have a few aspects of jargon here. One is the dialogue jargon. The other is the domain-specific jargon, and the informal speech. So it's kind of you need to somehow think about those stuff as well. And I just wanted to throw in an idea with the translation and to throw in some problems with the jargon so that you can think about them as well.
Yeah. So one thing that we do see, so we actually have a lot of clients who have multilingual situations. So basically every client in Germany also has to do, well, not everyone, but a lot of them also have this English use case. So far, it does seem that the way that they solve it is they don't do it by iterating on the model or the pipeline. They do it by iterating on the data. Mainly because, especially if it's customer service and it's for a brand, right? You really want to have a strict guarantee there. So it might just be okay to hire a translator if you're a multi-million-dollar company and it's really important to do customer service well. Who are you going to trust more? Like a person who's a linguist and speaks languages fluently, or an API?
Of course, yes. It's a question of priorities and money after all. If you
that's definitely accurate. But the iteration on data is an avenue that not a lot of data scientists really seriously consider, and it's something that I have found quite valuable.
Just to add to what Yasin gave as an example, I at least when I communicate with my colleagues, and I'm trying to talk data science in Bulgarian, but it never works. So you always tend to switch mid-sentence to English for just a couple of words and then back to Bulgarian. And you don't always switch the alphabets when you do things like that. So I'm not quite sure if people do weird stuff like that when you talk to a customer service chatbot, but I would imagine it would happen. And there is English comes into so many so I'm absolutely sure it happens for German customers because I've seen it and I've experienced it. Like mid-sentence, the customer just doesn't know the German word and goes into English, and then we're back into German for the verb at the end.
So the thing is, like this is also so every time people try out translation, it's so far the stories that I hear, it's a bit of a mixed bag. Mainly because translation is hard and it's an unsolved problem. But definitely the stuff that you're describing, I do recognize. I think it's called the bastardization of a language. It's happening to Dutch as well. So there's more and more English words suddenly coming in, and there's this weird moment where people say the English word but with a Dutch accent. So people used to call it a computer, but now they call it a computer, which is subtle difference. but it's exactly that. So I definitely recognize it.
Yeah, that happens often in Bulgarian too, but maybe it's even worse because sometimes people they just say the singular of the English term, but then they just add the Bulgarian suffix that indicates a plurality of this term, and then good luck kind of interpreting that with even the most sophisticated of models.
A question I just out of curiosity: if you're building an NLP pipeline in Bulgarian, what sort of embeddings and tools do you typically use? I've mentioned a few that I found, but I found them by Googling, right? So I'd love to hear if there's like tools that I'm missing.
I tried this once, training something for Bulgarian, and the thing that we did is just train embeddings using any publicly available Bulgarian text. So
you don't take the pre-trained ones; you just train your own.
Yeah, but this was like 3 years ago or 4 years ago. So definitely some things changed after that. So 4 years ago, it was like pretty standard to train your own word2vec or something like that. There wasn't a bird or transformers around, so you just
or Big Bird or any other Sesame character. Yeah, that makes sense.
But yeah, I think someone wrote in the chat that there are some pre-trained models right now, and as you said, there are byte-pair encodings in Bulgarian too.
Yeah, so byte-pair is nice because it has like 275 languages. So I mean, there's like 7,000 languages out there. So on that measure, it's still a drop, right? But you do know if you have 275, that odds are that you can at least offer one embedding to a person who's trying to do something.
Yeah. One thing that I'm definitely missing, and keep me honest, folks, I haven't heard of a stemmer for Bulgarian that actually works well.
Actually, so about that, I've added support for this tool called Stanza.
Yeah, the Stanford. Yeah, exactly. Yeah.
Have you? So I haven't. The only thing I've really used it for is tokenization, and I had one person who was Latvian who was trying it out. But if I go to models here, and I go to available models here, it says Bulgarian. So that's definitely in there. And if I look at the model performance, I think we can see that for Bulgarian, we have token sentences, words, parts of speech, lemmas. So you were interested in stemming? Sorry, what was it again?
Yeah, stemming was the one, but lemmatization would work actually as well.
Yeah, so it has lemmas, so that might be something that at least have a look at.
Yeah, similar. Yeah, good performance as well. Very nice.
You have to check the data set. That's the main thing.
Yeah.
I don't know what data set they exactly trained this on. But Bulgarian does look green compared to its neighbors, so go for it.
There is Boolstem. I'm not sure whether you used it. It's
How do you
not
spell
exactly recent, but
Boolstem?
Yeah.
B-U-L-N?
B-U-L-S-T-E-M, like from stemming.
Ah.
Yeah.
Yeah. I might be spoiled a little bit, but I remember it didn't have Python.
There is a Python. There
okay.
is a Python implementation of it, which supposedly works, but I never tried it.
It has 3 GitHub stars.
Yeah.
I mean, there's not this. It might very well work, right? I don't want to make fun of it, but it does feel it's a little bit young. Might be worth an experiment. Yeah. Okay. Bullstemmer. This is probably rule based, but usually that means that you can expect some form of consistency as well.
Yeah, I think so. I think it's rule based, but it's quite a large rule set, if I remember.
These rules are quite large. Cool. Okay. So I'm interested. So for Raza, considering I have the lemmatizer and the tokenizer, I would like to get feedback on those first for Bulgarian, just to see if that works. But those are neural based. So if people request it, I can maybe have a look if we can add something like this for Raza as well. Cool. Any other questions, or are we kind of tired? Because it's like an hour later for you folks, right? Yeltsin, you're muted.
Yeah, I was yawning. That's why I turned my microphone. I'm just kidding. I'm kidding. It's almost 10 o'clock here. Yes, it's. I think it's 1 hour. Yeah.
Okay. So then for everyone who listened, I mean, my name is Vincent. I work at Raza. You can Google me. There's packages out there. I'm the kind of person who, if you submit a ticket, I will definitely look at it. You will definitely get a response within a couple of days. If there's anything I can do to sort of make it easier for people to sort of try playing with chatbots in Bulgarian, I'd love to know about it. And if you're interested in learning Raza, hit me up. There's breakout bots and there's plenty of content.
And I have a question about PyData. First, how is PyData Amsterdam going? And second, do you have any general advice about PyData Sofia? What should we try? And,
so
yeah.
I have some advice. Like I actually don't do PyData Amsterdam anymore. People took over. I've done it for 5 years, and at some point I felt I'll do something else. So the thing that I'm the most proud of in Amsterdam is while I was there, I was able to sort of give it a little bit of identity. So I don't know, did you go to the last PyData in Amsterdam?
Not really.
So the last year I was there, I added 3 things. One was childcare. So if you're a recent parent, you can drop your baby off at the babysitter and you can still enjoy the conference. That's something we did. Made the conference way more fun because suddenly there were speakers we didn't get before and people visiting we didn't get before. So that was a good investment. The second thing that we did is we added a ball pit. So we actually found a ball pit sponsor. There was also a joke that someone took serious. I kind of joked at a sponsor like, oh, if all else fails, you can be the ball pit sponsor. The sponsor, that's an amazing idea. I'm going to totally do that. So we had to start.
Was there like a swimming HR agent in the balls? So when you go there, somebody starts, hiring you.
Well, so what we did was we had this ball pit in the middle of the conference, and basically teams that would sort of attend, they could have their photo taken there. But the thing is, everyone who went there has like a team photo in their office now in the ball pit at PyData. I mean, that's doing wonders for sponsors. that's and another thing that happened in a similar way, we also had a stroopwafel sponsor. So everyone that came got like these Dutch caramel cookies. We ended up getting like half a kilo a person. We got way too many. We got like a guy with a forklift bringing in half a cubic meter. We got like it's pretty funny. But because of this sort of attitude and this vibe, right? London's a bit more formal. It's a bit more finance. It's the Brits, right? So stiff upper lip. It's that culture. But the Amsterdam event kind of got known at some point for, it's a smoke and a pancake. Half of the talks there are not necessarily about things that are super like academic, but usually someone tries to over-engineer something and it totally failed, but there's a lesson there. Those are the kinds of talks at some point we got really good at. So there was this, and that's the best advice I have for getting speakers. There was this one person and he gave a really, really cool talk. So one keynote speaker was talking in the small room in London, and he was talking about how it's his hobby to look for endangered species of orangutan using drones. and basically, I come up to the guy and said,
"That's very specific."
That's really specific. This is awesome. Like there's bound to be something you learn. It was super inspiring as well. So I just walked up to the guy and said, "Look, you got to be a keynote. Sorry, like you shouldn't speak at the small room. You should come to Amsterdam. I'll just give you the keynote." And we did. It was an amazing talk. You should watch it. But similarly, there was this other person who had a blog, really cool blog. It was super silly, but he had this sort of Markov chain where he was trying to figure out so he downloaded all the metal lyrics from like metal albums, and he was trying to figure out which word was the most metal and which word was the least metal. And he gave a talk on just this. But he over-engineered it. Like he took this kind of silly thing super serious. But those talks were amazing. But the thing was, he never realized that could be a conference talk. He kind of saw it as a blog post. It was kind of cute. Maybe a couple of people read it. He didn't fully realize that's totally a legitimate topic for a talk. So the best way to get speakers is just to recognize like, hey, this is a cool blog post. And then you walk up to someone and say, hey, you should realize you can totally talk about this. Please come to my meetup and talk about it. It's usually the people who have like, it's introverts in our programming space that don't necessarily know that they're doing something awesome. These are the speakers you want to get.
Yeah, great. That sounds like a great advice. I've tried with a few, but they're like, I don't want to speak in front of people, So
Get them as a lightning talk.
Yeah, that's a good idea. Yeah.
We've actually done meetups with only lightning talks, which are pretty interesting as well. So it's everyone just gets 5 minutes, and sort of if you're at like 4 minutes 40 seconds, we start clapping with one finger, and then it's 4 minutes and 50 seconds. We start clapping with 2 fingers, and then you're essentially booed off the stage if you're not doing it. But also that has a really cool vibe to it. And again, the goal is to have people recognize that they probably have something super interesting to talk about. They just don't know it yet. We had a guy talk about JSON parsing. It was amazing. Because this person went to like super low level stuff, which no one else would do, but he did. Great.
Yeah, these are great advice. I'm actually taking notes about that, so we'll try that.
Another thing that you can also do is like you have to. Hopefully, Corona will be over, but probably not. There's also PyData Global that's happening. So there's like people from all over the world doing talks and stuff. It might be nice to sort of see if you can do a collaboration with that. All the money there also goes to NumFocus, and even though it's not physical, like people will be sending pre-recorded talks. If you buy a ticket, you're going to see something that's super funny, because this morning I finished my talk. Like I recorded the last 2 minutes, and I did that after I shaved, not realizing that all the recordings before had like me with a beard. So if you're interested in how I rescue, sort of how I fix that situation verbally, definitely go buy a ticket for PyData Global. It'll be fine. But it's just this. Like a lot of people have cool stuff to talk about. They just don't know it yet. That's the main thing. And another thing that you can do that is kind of interesting is just sort of make like a challenge where you can pick a theme. So video games typically are pretty good. So go to a bunch of students and say, look, we're just interested in someone kind of as a competition who can tell us the coolest thing about a video game. This way I calculated how big the 1% of